experiments. Then we tried, some of people working in the 3D printing community. This was from a work by the group of Gideon van Zyl and Jacques Kruger at University of Stellenbosch in South Africa. Was this kind of brick wall, I would say. The printing process was quite nice. We predicted also, you know, the number of layers, how the yield stress evolves, because we included thixotropy. But one interesting information that you can get, you can see from here. You see that we have a dark gray zone is where the material is fluid, is flowing, you know, because it's, you know, the stress is higher than the yield stress. So when you print intersecting filaments, you have to locally overcome the yield stress, because that guarantees you some compenetration of the material. If this does not happen, you will have a cold joint or an improperly joined in your element. So this is something that a numerical tool can help you having an insight into. And now, well, you know, we are trying to go into more complex shapes. You can see here some examples of how our tool can work with complex objects, you see here. And also you see that only a small part of the material is really fluid. The other one is already, let's say, solid-like, because the stress is then below the yield stress and does not move at all. And you can see some also elastic adjustment, I will say, of the shape of the elements when you print. And investigating the influence of the yield stress, our tool was also able to show if the yield stress is too low at a certain point, it will collapse under its own weight because of a mixed plastic failure and elastic buckling one. So just going into the conclusions and further outlook. So what we have worked in, I will say, in the last 4 years is to develop this finite element solver based on arbitrary Lagrangian Eulerian approach to reproduce, to design the 3D printing process, and we have validated it against experimental data for cementitious materials, and helps us to, you know, analyze in an effective way instead of avoiding trial and error tests, because if you need to do this experimentally, it will require much more time and much more resources. We are applying now to complex realistic printing scenarios, and we have also developed this, you know, mixed artificial intelligence tool to predict the shape of the printed elements. The acknowledgement goes to the 3D printing people in our lab. And also I take the chance to advertise, there will be quite some talks on this topic and posters in this conference, the Gordon Research Conference that we are hosting in Italy next February. If you are interested, drop me an email. We still have slots for posters. The program is already set, but we have slots for discussion and for posters. And as a matter of fact, this is just my last slide. You can find us in LinkedIn, email. There is the QR code for our tool. These are our papers. And I thank you for your attention.
Excellent presentation, Professor Liberato. And this presentation on time. And then any quick questions, if you have any doubts, quick 1 or 2, if you have particular. Yeah.
Limitations on the magnitude of the structures?
Well, that is, the limitation is only due to the computational power that you have. So far, we are working with Technical University Eindhoven, and we are modeling walls that are a couple of meters in width and about 1.5 meters in height.
Only for the models?
Yeah, it's just the computational power. Now we're using parallel codes and so on in order to speed it up. So it's a matter of computer power, of CPU power that you have. But there are theoretically no limitations you can use.
But really, whether we can implement the structures?
Yeah, we are doing that. We are studying real scale structures up to meters scale. Yeah.
Thank you. One more last question, quickly. One from student.
Sir, that was a really great presentation, sir. I have a small question. Is the nozzle height to the standoff distance ratio accounted in the simulation?
Yes, yes, yes. In this case, we kept it the nozzle to weight equal to 1, but you can change it.
Okay.
Yeah, yeah. It's one of the parameters that you can change.
Okay,
Yeah.
because that may affect
Yeah,
the
yeah,
shape
yeah.
and
We also,
the-
and in the parametric analysis, we changed it. We
Okay.
changed it because it's one of the parameters that you have varying. Yes, that's true. Yeah, for sure.
Thank you, sir.
I think one last
Thank you.
question we can have from there. Yeah. Let's allow her.
So I was just very nice presentation, sir. I was very curious to ask, this type of cement requires like a rapid setting type of this thing.
Well, as a matter, in our case, we used only one component, so we did not have the 2K system. But obviously, the rheology, you have to adjust it in order to have, you know, the rapid development of the yield strength that you need to print at least a couple of layers. And, you know, you can rely on thixotropy that helps being up the structure, the internal structure of the material. Yeah.
Thank you so much, and excellent presentation. That too, he has developed a deep learning tool and validated, so we could able to see that. Okay, thank you so much, Professor. Yeah.
Thank you, sir, for the presentation. We have a token of appreciation from the organizing committee. I request Javinder sir to hand over the move.
I request Professor Manu Santanam sir also.
Please join. Sir, can you please join? Actually, I don't know your name, sorry.
So we have 7 presentations. So the first presentation, without any delay, we'll be calling the first presenter on topic optimization of nanomaterial characteristics to achieve self-sensing concrete, part DS. So you have like 8 minutes for presentation, 2 minutes for question and answer session.
So, good afternoon, everyone. I am Suresh Kumar Pahadi. I am from Bir Surendra Sai University of Technology. So, I'll be presenting on my technical paper on optimization of nanomaterial characteristics to achieve self-sensing concrete. So, outline of the presentation starting with introduction to self-sensing concrete, methodology, data analysis, prediction and optimization. After that, post-hoc analysis and conclusion. So generally self-sensing concrete embeds pillars, like conductive pillars like nanomaterials to sense the to create the percolation network in cement matrix. Under this mechanical loading, these networks generally tends to break, and it changes the electrical property of the concrete, which can be measured to know the sensing or to know the damage of the structure. So to measure this self-sensing mechanism, there is mainly 2 types of measurement is happen. That's the piezoresistivity-based sensing and piezo-permittivity-based sensing. In piezoresistivity, the changes in resistance is measured. In piezo-permittivity, there is changes of capacitance or dielectric constant changes are measured. So in structural health monitoring, generally piezoresistivity-based sensing is ideal, so we have optimized the studies optimized the piezoresistivity sensing based on nanomaterial characteristics. So going on to the methodology, so we have first developed a data set from the available literature regarding this piezoresistivity sensing, And further that, we have analyzed the data set and then trained the machine learning model to predict the properties like electrical resistivity, compressive strength, gauge factor, and cost. So these models are trained as objective function to optimize the nanomaterial characteristics. So 200 different data points are collected from the literature. Nanomaterials considered are carbon black, which is 0-dimensional, carbon nanofiber, carbon nanotubes, which is 1-dimensional, and graphene nanoplates and graphene oxide, which is 2-dimensional nanomaterials. So these are the data contains nanomaterial doses, its particle size, lateral size, and distribution, aspect ratio, water cement ratio, and the outputs we have considered compressive strength, electrical resistivity, gauge factor, and cost. So after collecting the data, we normalize the data set before going into modeling. So we consider 3 machine learning models, that is random forest, XGBoost, and multi-layer perceptron. These are machine learning models which used to generally capture the nonlinearity of the database. So we did the 10-fold cross-validation method for training and testing. See, these methods are used like the dataset is divided to 10 parts, and in every part we'll be training the data is divided. We'll be training the models 10 times. So with each 9 parts of the data will be used for training and one part for testing. It will be continuously going for 10 times. So after training these machine models to predict the compressive strength, electrical resistivity, gauge factor, and cost, we found that random forest model outperformed other models in prediction of compressive strength, electrical resistivity, but in gauge factor, XGBoost outperformed all models. But in cost related, the machine learning models didn't perform well, so we choose a polynomial equation as objective functions. These objective functions used for optimization process using NSGA2 optimization framework, which is the evolutionary optimization framework. These machine learning models used an objective function to, we have done 2 kind of optimization, that is bi-objective optimization and tri-objective optimization. In bi-objective optimization, we have decreased the electrical resistivity and increased the compressive strength. And tri-objective optimization, we have decreased the cost and electrical resistivity and enhanced the compressive strength. In generally ranges between compressive strength 30 to 45, we found that there are more sensing ability of concrete. So after optimization, we created 150 around optimized solutions. This mix we analyzed for different characteristics of nanomaterial like aspect ratio and contents and the gauge factor, lateral size. So generally high aspect ratio nanomaterials provide more gauge factor and more sensitivity. That is due to the 1-dimensional nanomaterial like CNTs. And with optimal lateral size of 2 to 6 micrometer, generally due to 2-dimensional nanomaterial like graphene oxide, they provide a higher sensing ability. So in cost related and strength related, we found that CNT and graphene oxide related concretes provide more strength compared to other nanomaterials. And cost wise also, these CNT and graphene oxide and graphene nanoplates provide more cost compared to other nanomaterials. So these are the conclusions. The shape and size of nanomaterials strongly influence the performance. So sensing mainly depends on particle size and aspect ratio. High aspect ratio fillers create conductive paths at low doses, improving gauge factor and strain sensitivity. Larger lateral dimensions support better load transfer and mechanical strength. Geo and CNT show the best overall behavior apart from the high expenses. Large scale synthesis can lower the material cost. Thank you.
Very good, Padri, on time. Quickly finished your presentation. Any quick questions? Only 1 or 2? Yeah.
So it's a good presentation. My question is like, what is the minimum percentage of CNTs that you need to add so that you can have a self-sensing properties?
Around 0.5 to 1%.
Okay.
For graphene oxide, it will be 0.05% around.
Okay.
But the CNT it is more higher. But the thing is that CNT does not interact with cement matrix well. So you have to functionalize that CNT using OH functionalized groups so that it can easily interact with cement matrix.
Any more question? Okay. One last, because nobody is asking. So your model, ML model, is not predicting cost properly. Like, you know, later you depended on something. Can you put, you know, 1 or 2 lines on that? Why and what may be the reason, something like that?
I don't know, maybe non-linearity or something, but I didn't perform well.
Okay, maybe further you can work on that.
Yes.
Thank you so much, Paddy. Okay. Next presenter. In situ monitoring of printability of alkali activated binder in 3D concrete printing using the embedded smart PZT sensor by Dodi Murli. Yeah, go on.
Okay. Good afternoon, everyone. Myself Murali Duddi, a research scholar from IIT Hyderabad, and my co-authors are Humendra Singh, a master student at IIT Hyderabad. We are working under the supervision of Professor KVL Subramaniam at IIT Hyderabad. So the title of the presentation is Inline Monitoring of the Printability of the Alkali Activated Binder in 3D Concrete Printing using Embedded Smart PZT Sensors. So as you all are aware that the concrete 3D printing will be a revolution in the concrete industry because of its various advantages such as faster rate of construction, customization, optimization of the structure that you want, sustainability and cost efficiency. Whereas the 3D printing is morely like the first parameter that you need to come up is like developing a printable mix. And it is also important to know what are the properties of the printable mix so that you can have a proper printing. And typically the 3D concrete printing has 3 processes like pumpability, extrudability and buildability. All these 3 properties are majorly governed by the yield stress and viscosity of the material. So there is no direct methodology or technology that can monitor the yield stress and viscosity of the material in the field while printing. So this needs a local sensor which can sense the material property. So there comes a piezoelectric based sensor which will be working on the physical measurement of the medium. So what PZT is? PZT is basically a piezoelectric material which works on the principles of piezoelectric effect, which relates the stress and voltage. So if I take a PZT patch and apply a pressure on it, it will start to generate voltage. Vice versa, if I apply voltage and it will be strained. So typically the piezoelectric constitutive law is a relation between the electric field and a stress which gives you a strain and electric charge density factor. So if a piezoelectric material is taken and a voltage is applied by varying the frequency, then PZT starts to vibrate. It will lead to generate the charge on the surface of the PZT patch. The surface integral of the charge gives me a current. The ratio of the current and voltage gives me an admittance. Typically it is a complex number. It will have a conductance as a real part and susceptance as a imaginary part. So for a 20 mm PZT, 20 mm dia and 1 mm thick PZT patch, this is typically the admittance signature, and this is the conductance signature which is a real part, and this is the imaginary part as susceptance. So you can clearly see a 3 distinct mix within the frequency range of 20 Hz to 500 kHz for a 20 mm PZT patch, and those are identified as the resonant mode of vibration of the PZT patch. And this is the first mode of vibration, which is a radial mode, and this is the second mode, and this is the third mode. All the 3 modes of vibrations are more of a radial mode, but the complexity of the mode of vibration with increase in the frequency. So now we understand what PZT and how it works. So in order to use this for monitoring the properties of the material, so what we will be doing is like when the PZT is in air, whatever the resistance offered to the free vibration of the PZT is just air. So there is not much resistance to the free vibration of the sensor. The moment we place inside the concrete, the vibration of concrete or any cementitious material, the vibration of the sensor depends on the mechanical impedance offered by the medium. So it is going to reflect in the electrical impedance measurement that I am going to capture from the sensor. So if I can monitor the changes in the electrical impedance response of the sensor, I can monitor the changes in the mechanical impedance in the medium. So, but the problem here is typically this piezoelectric material is a electrical component which will get short circuited the moment we what is come in contact with the PGT patch. So it needs a protection scheme. So what we have done is to develop a embeddable piezoelectric sensor, we have taken a circular PGT patch of 20 mm dia and 1 mm thickness and applied a epoxy coating on the PGT patch using a spin coating technique to have a uniform thickness. It will help in getting from short circuiting and also any physical damage during in concrete like vibration or any impact, something like that. So and further we have applied a 2-component hydrophobic coating, which is an aerosol on the surface of the epoxy to protect the epoxy layer. So this is the photograph of the sensor that we have developed, and this is the typical impedance response of the sensor that we have developed. And coming to the study where we want to see like how the sensor can be helpful for me to check whether the mix is printable or not, I have varied the different compositions by keeping the solution to binder ratio as 0.4 and varying the rheology modifiers such as bentonite and CMCs. So you can see in the starting where the mix is completely flowing when I don't have any rheology modifiers, and by altering the rheology modifiers I was able to get a mix which is completely buildable and stable. So coming to the test setup where I have taken a 3D plotter for printing this material, and we have placed a sensor at the close to the ram, that is at the barrel, and the sensor was connected to a LCR meter to extract the impedance measurements. And the test program where we have varied the frequency range from 100 kHz to 150 kHz, which is where the first resident mode of the sensor will be working, and we have collected around 200 data points, and the measurements were continuously taken during the printing. And coming to the characteristics of the various mixes that I have considered, like they have named it as B02, B03. In the starting mix where it is completely, where we don't have any rheology modifiers, there is no buildability, shape retention, there is water migration is there, and cracking also, no cracking because it's completely flowing. When it comes to the last mix where B3, where I have the buildability, shape retention, and there is no water migration and no cracking was observed. So in all the cases, I have taken the impedance measurements from the sensor, and this is the measurements from one of the mixes, like the final mixes I can say, where we have taken the measurements at every 1 minute interval during the printing. So if you observe, there is a continuous drop in the magnitude and the shift in the spectrum is observed. So in order to quantify, consider the peak value drop and the spectrum changes, we have done a statistical measurement like RMSD value by comparing the initial sensor response before placing in the mix, and then we have observed that as the consistency of the mix is increasing, like the buildability of the mix is increasing, there is an increase in the impedance value, and it has kind of a flattened because there is the time gap is hardly a 10 minutes. It is not going to affect the change in the material properties that much. And then to normalize the effect of the mix as well as the sensor's response, because every time when I'm going to place the sensor, it should not be altered. So to normalize that, we have come up with the impedance ratio where the peak impedance for every interval will be taken, and it is divided by the impedance of the base. Base means like before placing inside the mix. So what we have observed is the mix which is having a more buildability and shape retention, the impedance ratio is very, very less. And we observed that the mix with the impedance ratio around 0.4 to 0.45 is able to have a good buildable properties and pumpable properties. So coming to the conclusions, we are able to develop a sensor which is sensitive to monitor these mix properties. At the RMSD values are like minimum for unstable mix, and it gradually increased as the stability of the blended mix is enhanced. The impedance ratio decreased with the enhancement of printability and durability of the mix. And finally, the mix with impedance ratio closer to 0.5 has shown a printable characteristics. Thank you.
Thank you, Murli. On time, quick presentation. Any questions? Quick questions from audience? Yeah.
Yes.
1 second.
on the deck is like that convention.
Murli, nice presentation. One quick question about the placement of the PZT sensor. So now it's placed at the bottom of the plunger. Now, again, the pressure of actually the pushing the material through this plunger is going to obviously affect this. So that pressure is what you're relating to the rheological characteristics of the concrete that you're pushing, right?
It's kind of like, because it's completely within the medium.
Yeah.
So like that is like we are kind of going in a trial and error where I have to exactly position the sensor.
Yeah, that may be also another reason why your variation is very limited. I think it's only within 1 kilohertz. Your impedance variation is quite small there.
Yeah, there are two things I have to consider. One is like even if I go for a yield stress variation with the time, even it will be like when it is kind of a compacting,
Yeah.
it will be increasing the yield
Correct.
stress, and then it's more of a plateau.
Correct.
I have not taken the measurements, so actually it is kind of compacting. It is only when it is kind of
It's
fitting
fresh.
completely
Okay.
extrusion. So it is more of representing what the yield stress that I am kind of getting. It's like yield stress is also kind of plateau when it's kind of bending. So similar phenomena I kind of observed, and even like you said, near the crust, definitely if I take this force equilibrium conditions, it's more like whatever the pressure that I am applying from the top, it's going to experience the more or like the same. So I'm kind of looking at when there is other locations where I can kind of observe this flow, like when it is like shaping effect is going to come and on.
Murli,
Maybe just the
specifically, sir
sensitivity.
was saying the sensitivity of sensor, of placing, so you may have to work on it.
I think the idea is very good. Maybe that sensitivity development can be.
So with that, thank you, Murli. Any other questions? I don't think. Two more.
It will be working. If it is vertical, then how it will work?
Whatever that is like, whether it is vertical or horizontal.
If it is in this position only, it will work. If it is like this horizontally, then how it will work? Even placing through the very difficult concrete, how you maintain it?
So first thing is like whether whatever the orientation of the sensor, it is not going to affect the impedance response, because whatever the response the sensor is going to give me from the electrical impedance measurement, generally we are vibrating the sensor, like applying the voltage. So it continuously vibrates, and the response depends on the properties of the medium, like whether it is in horizontal or vertical. So because I'm not looking at.
So that's what your question is same, like, Professor already asked the position of, the sensor and then its effect. Anyway, you can discuss during the, tea time. Thank you so much, Murli. I think our next presenter is the effect of precarbonation duration on CO2 uptake on pH for OPC cured cement paste by Charita. Yeah, over to you, Charita.
Good afternoon, everyone. I'm Charita. I'm a PhD scholar at IIT Hyderabad. From yesterday, most of you have heard a lot about carbonation curing. What are the effects of it? So today, in my presentation, I'll give you a detailed review of what exactly carbonation curing is, how are you gonna do. So in this today's presentation would be on effect of precarbonation duration on CO2 uptake and how is the pH varying in this carbonated samples. As we all know, 1 ton of cement produces approximately 1 ton of CO2. So in order to reduce the CO2 emissions during the production, we use different alternative materials, or we have to go up with usage of alternative fuels, also there can be waste heat recovery, and we can do carbon capture from this. Approximately only 20% of the emissions in the cement industry are being captured. How can we utilize them in construction industry? We can utilize them in precast industry by carbonation curing, and in ready-mix cement industry also by carbonating the recycled aggregates. What exactly carbonation curing is? Subjecting the early age specimens to high concentrations of CO2. This is a 3-step procedure starting with preconditioning. In preconditioning means the moment when you add water to the cement, the preconditioning starts. It includes in-mold curing, and in some cases it includes air curing as well. Then follows carbonation curing, where the specimens are subjected to a particular concentration of CO2 for a particular duration, where in few cases relative humidity is controlled and temperature pressure is also varied. Next comes post-carbonation curing. After carbonation, the specimens are subjected to carbonation. The samples are subjected to water curing. What exactly happens inside when you subject a sample to CO2? It diffuses inside and dissolves, and it starts reacting with the hydration products. So you can see, so you will, there can be a direct reaction with the C3S phases with CO2. Also, there can be a direct, the hydration products that are formed can react with CO2, forming carbonation products. Along with carbonation products, we see hydration products as well. In the study, I would like to determine the effect of preconditioning duration on CO2 uptake, and understanding the effect of air curing on CO2 uptake. I'll end up with what is the, how is the pH evolved during the, over the time. So in this, I've considered a cement paste sample, which I have been subjected to CO2. In this, for the particular paste sample, on the paste sample, I've done CO2 uptake and pH tests at 1 day and 28 days. So in this study, I have varied pre-curing durations as 6, 9 hours, 12 hours. Along with that, for 6 hours of in-mold curing, I've included 3 hours of air curing as well. Also for 9 hours of in-mold curing, I have included 12 hours of 3 hours of air curing and 12 hours of carbonation curing, and the samples are subsequently subjected for water curing. So these are my TGA results for 1 day and 28 days. I'll first focus on 1 day TGA results. So we can see that I don't, particularly at 400 to 500, the specimens that are subjected to carbonation, there is no calcium hydroxide, which is a well-known fact, that the calcium hydroxide has been converted to calcium carbonate. Now if we see how is this being varied, how is the precarbonation effect influencing on CO2 uptake? We can see that with increase in precarbonation duration, the CO2 uptake is also increasing. And specifically for 6 hours of in-mold curing and 3 hours of air curing, the CO2 uptake is increasing compared to 9 hours of in-mold curing. Now coming to 28-day TGA results, in the sense I've subjected the sample for 12 hours of in-mold carbonation curing, and then I've placed them in lime water till 28 days, and then I've done TGA study in this. So even after 28 days, I don't see any calcium hydroxide formed, which means that there's no further hydration that has been taking place in this case. Also, one another reason that I think it can be is this calcium carbonate that is forming is being coated on the surface of C3S or C2S, which is hampering the further hydration. Also, I determined the bound water and calcium hydroxide in these particular cases. In control samples, in the samples that are demolded after 24 hours, I see increment in calcium hydroxide and bound water, but in the samples specifically with carbonation cure, there is no increment in calcium hydroxide and bound water. Coming to the CO2 uptake, I see a tremendous increment with increase in precarbonation duration, but is it actually helping us in over the long term is a real question. Coming to pH, the control samples showed pH around 12.25 something. whereas the carbonation samples, it was around 11.5 to 12. It was in that range. Even after 28 days of water curing, it was in the similar range, which means that there is no effect of water curing in the later stages due to carbonation. So I would like to conclude that the CO2 uptake increases with pre-carbonation duration, indicating that sufficient drying improves carbonation efficiency. Also, when we subject the samples for carbonation curing, the internal RH is reduced because it's an exothermic reaction. So that can be the reason why there is not sufficient water inside the system and further hydration is not possible. Also, pH is decreased in carbonation-related mixes, but it remained above 11, which says that the steel passivation is still not compromised. Thank you.
Thank you, Charita. Any quick questions? One or two? Yeah.
Yeah, thank you, Charita.
Yes,
Just a quick comment about the fact that you talked about the hydration being hampered by carbonation. Now, how big are your specimens that you've chosen?
I wanted them to be completely carbonated.
Yeah.
That's why I wanted to see if they are completely. So I used around 6 mm samples.
Okay.
The thickness
6
is 6 mm.
So obviously,
Yes.
they were entirely carbonated during this duration, right?
So I wanted to understand the phenomena. So if, say, in case if I'm doing it on mortar or concrete level, the top surface gets carbonated especially.
Right.
So there won't be any chance of further hydration in the top layers, but it gets denser. So how is it reacting? So I wanted to understand that phenomena. So I made sure that the sample is completely carbonated.
Okay. Sure.
Maybe I feel like, it's a suggestion, because most of the time we go for the cover, okay? Maybe the cover thickness, at least if you would have used for the samples, maybe. Yeah, because we do, maintain the cover for various members. So when you take the cover as the, thickness of the sample, we'll get the more clarity on the carbonation part. Maybe the suggestion.
But when I tried using...
No, at least 20,
I tried
25.
with 20 mm. I tried with 20 mm, but
Okay.
the carbonation depth was not completely, it was not completely carbonated.
Okay.
So it was difficult for me to take sample only from the carbonated area. So
Okay.
that's why.
Anyway, thank you, Charita. Our next presenter, in situ resource utilization for sustainable 3D printed construction using locally sourced construction materials. Modi H. Yeah.
Good afternoon, everyone. I am Prashant Singh from IIT Hyderabad. Today, I'll be presenting on behalf of Hanuman Nayak from Simpliforce Creations. He is head in R&D Materials and Composites. So, the presentation topic is in situ resource utilization for sustainable 3D printed construction.
So basically, you're a co-author, right?
Yes, sir.
Yeah, yeah. So anyone.
So the problem statement here is the industry technology stagnation. As Professor Liberato Ferreira said, there is no much innovation going on in the field of construction. Then housing crisis that we are facing in Indian market. Then inaccessibility to remote areas such as very high altitude areas and remote places. And terrain specific construction like in high altitude or very less humid areas, we have to adjust our mixes and designs according to that. Also the design and manpower limitations. So these are the problems that we are facing in construction industries. To overcome that, the solutions that we provide from 3D printing is the elimination of farm work, less workforce, design freedom, customization, sustainability and time saving. Also the material saving that we see in this technology. So as we know, the 3D printing is a process of layer by layer additive manufacturing process in which we print the structure layer by layer and eliminate the formwork that in traditional construction is required. In 3D printing, it's not required. So it's also very rapid construction, and complex geometries can be made. Also, we can use it for bridges, defense structures, and architectural elements. So the workflow that is followed in this process is first is design input, then structural design, slicing, mass customization. Like there is freedom of customization, shapes and forms. Then this file is further uploaded to digital software, and then selection of material. And there are two processes, ex situ and in situ printing. So ex situ is like printing in off-site, like precast elements, and then it is shifted to the site and assembled, or the whole structure also can be, if it is small, can be shifted. And on-site printing, as we can see here, the world's first 3D printed temple is printed at Siddipet. So I would like to highlight the mix that is patented by Simpliforge Creations. It's called Simplicrete, which is like made by using locally available materials, which offers around 40 to 60 MPa strength. So our objective was to develop a like mix using locally available sand from Srinagar, and we compared it with well-graded sand which was available in Hyderabad. So the objective was to assess the extrudability, buildability, and rheology of the mix. So, and to demonstrate the in situ resource utilization based construction in variable environments. So we used two types of sand from Hyderabad and 3 types of sand from Srinagar. And Hyderabad, we were able to get OPC 53 grade, but in Srinagar it is not available. So we were not carrying the material from here to there. Whatever is available there, from there, that only we printed. So these are the particle size distribution of sands from Hyderabad and Srinagar. So the mix ratio that we used was is mentioned here. Little bit, mostly the water to cement ratio was kept constant. Just the admixture dosage was varied according to the silt content present in the sand, which was very high in Srinagar's sand. So from Hyderabad mix, we found that there is some mistake, I guess. Sorry. So with first mix, we got about 35 layers of buildability, and the second mix we got 44 layers of buildability. And the Srinagar sands, we tried with different admixture dosage and different aggregate proportions, and found that it was about 30 to 35 layers of buildability. So the key observation was the sand gradation strongly affects the rheology and layer stability. Finer sand with controlled silt improve interlayer bonding, and optimal admixture dosage of around 0.33 to 0.36 was sufficient to balance the flowability and green strength of the mix, 3D printable mix. And this demonstrates that local sand can be adapted for reliable 3D printing performance, and in situ resource utilization enhances the sustainability and logistics flexibility in remote regions. So conclusion is like the Hyderabad sand were having best printability, but Srinagar sand also was best according to that location. Buildability achieved was around 30 to 44 layer, where 30 was for Srinagar sands. So future work can be like we will perform mechanical testing, durability, and microstructure of the printed elements. So thank you.
Thank you, Singh. I think more of application-oriented work. Any questions quickly? Any questions from audience? No? Okay. So the gradation, I have a question if nobody asks. So gradation part of sand in both the areas, like there in Srinagar and here,
Yes,
is the silt content, because silt content here in Hyderabad sand,
yes,
you showed more. Is there any effect on the printability?
No, Hyderabad sand has had less silt content,
okay.
And
That's
Srinagar had more, so
okay.
it affected the mix. Like we had to use more admixtures to control the rheology, and also it affected the bond because it had silt, which made the layers bond well for that. But the rheology was affected, so we didn't got much buildability from that.
Okay. So basically, Srinagar sand has got more silt, so you could not able to print
more layers.
More layers with that. Okay, thank you. Any more questions? No? Okay. Let us go to the next presenter. Yeah, thank you, Singh. So we have with us next presenter, Mr. Gopalar. He is going to present on ultrasonic imaging for crack depth measurement in concrete using ultrasonic shear wave tomography. Yes. Over to you.
Good afternoon to all. I'm Ramesh from CSIR Structural Engineering Research Center. My co-authors are Vivek and then Professor Manu Santhanam and Dr. Bhaskar. And then what I'm going to present today is ultrasonic imaging of crack depth measurement in concrete using shear wave tomography. Basic introduction: concrete structure may lead to crack due to loading and then environmental effects, and then it may due to shrinkage, or it may leads to cracking. Because of cracking, the atmospheric agents like carbonation, chloride will go into that reinforcement and leads to corrosion. And then it is very, very difficult to quantify the crack depth in concrete. Even crack width can be measurable. The depth of the crack in concrete is very, very difficult to measure. Even many techniques are available, but it is very, very difficult. It is qualitatively only can be measurable. Quantitatively, it is very, very difficult. And then that is the limitations. And then traditionally, crack depth measured using visual inspection, and then visual inspection, crack depth cannot be measured visually where the crack is, what type of crack that can be addressed. And then core drilling can be a method, but it is a destructive method. People are not following it. Through conventional UPV, crack depths are measured, but it is not qualitatively measured. And then some more measurement techniques, advanced measurement techniques like impact echo, all these measurement techniques are available in the market, but it has got limitation in concrete. That is what we feel. And then even in ultrasonic also, Rayleigh wave method is there, but Rayleigh wave has got some limitation due to reflection boundaries effect. The Rayleigh waves will measure the surface effects, near surface effects only. It will not go beyond that. That is the limitation of the Rayleigh wave. So that is the need for a need for reliable subsurface crack characterization. For that, we have taken concrete specimen of size 1 meter by 1 meter by 200 mm, and then 1 meter by 1 meter by 400 mm slab we have taken. In that, we have artificially simulated a crack depth of 50 mm, 75 mm, 100 mm, 150 mm, 200 mm. The crack width is 1 mm. That is what we have taken. And then for that simulating, we have taken a metal sheet. During concreting, we inserted that metal sheet. Once it is getting hardened, we have removed that crack width. We have removed it, and then we have removed it. For that, we used M40 concrete. You can see the schematic. This is how we have placed the different crack depths in a concrete specimen. For that, we have used ultrasonic tomography. Why we went for ultrasonic tomography? Conventional ultrasonic is purely based on P wave techniques. Here we went for a shear wave techniques. The advantage of using shear wave technique is there is no mode conversion in it. Whereas the conventional ultrasonic methods, you have a mode conversion. Here it is purely, it's a shear wave. If you go for another wave methods like P wave, there will be a mode conversion will be there. P wave is getting converted into a Rayleigh wave, and then shear wave. All combinations will be there. Whereas in a shear wave tomography, it is a shear horizontal shear wave only will be there. That is the reason for choosing this shear wave tomography. For that, we have used a Mira A1040 equipment. It has got a 48 element shear wave array of transducer, and then this is purely a dry point contact method. Conventional ultrasonic, you have a couplant, whereas you don't require any couplant in this. That is the advantage of this. And then even uneven surfaces also you can place it, and then it has got a spring loaded transducer in it. It has got a 48 transducers. It's an array of transducer. One will act as a receiver, one will act as a transmitter, other will receive. Like this sequentially it will operate. The method in this is the pitch catch method. And then this is the in tomography you'll get A scan, B scan, C scan, D scan. When you are placing this tomography in a structure, here especially we used in a crack depth, in a cracked specimen, you have to place this tomography in a perpendicular direction. If you place this perpendicular direction, you will have first you will get a scan, and then it is perpendicular to the measurement, you will get a B scan. Below that you will get a C scan measurement. This is how it will capture the measurements. And then for these two methodologies we have adapted for measuring this crack depth. One is called line scan method, another one is called area scan method. This is how we have formulated a methodology to measure a crack depth in a reinforced concrete. First one is the line scan method. The tomography is placed perpendicular to the crack. And then series of scans we have taken at an interval of 30 mm interval. We have placed this tomography, and then we have taken the readings. This is how we have taken the readings. And then what it will record is, it will record the time of flight measurements. From that we can able to get the velocity. From that you will get a time of flight. From that you can able to image it, and then you can see the crack, where the crack depth is. Basically the line scan is a faster method when compared to area scan. The limitation is it's purely a one-dimensional method. And then this is the area scan method. Similar way we have area scan method also similar to line scan, but whereas the methodology we have used a serpentine curve like this we have used for get a three-dimensional representation of crack depth imaging. This is how we have executed the measurements using tomography. This is a typical slab with measurements taken. For that, in this tomography, the algorithm what we are using is SAFT algorithm. SAFT is nothing but synthetic aperture focusing technique. It's a digital signal processing technique used in NDT measurement, especially for concrete applications. What it will do is, during the measurement in tomography, series of A scans will be collected. The series of A scan will be collected, and then will sum it up into a B scan. B scan will give the image representation. From that B scan, C scan will be computed through this algorithm, and then C scan also will be computed with this algorithm. What it will give is the synthetic apertures produces a clear 2D and 3D images of the internal defects. Whatever, in this case, we have taken it for crack depth measurements. With this equipment, we can do a rebar detection, flaw detections, all those can be possible. For this case, we have taken it for crack depth measurements. This is how the SAFT algorithm works. If you place a transducer over a crack depth, series of shear waves will be imposed over the crack, and then it will be summing it up into that synthetic aperture algorithm. The whole images you can be focused. The advantages of SAFT algorithms, it will give a sharper images, enhanced defect visibility, suitable for reinforced concrete. This is how results of line scan. For 50 mm, 75 mm depth, you can see approximately the crack depth will be measured. The two red lines are the back wall reflection. Back wall reflection is nothing but the depth of the specimen. Above that, you can see near the 50 mm scale, you can see the crack depth. Even C scan, D scan, you can see the clear horizontal line shows that the crack depth is throughout that. That is what it gives. The depth of the crack approximately will be around 55 to 60 mm. Accurately, it will not estimate. There is some limitation in that line scan measurements. And then you can look at in the 3D images also, even we have graded the sections, and then you can see near the crack depth measurements, there is a crack depth, there is a continuous crack depth can be visible. This is how it works. For 150 mm crack depth also we have, and then 200 mm also we have measured. In 200 mm you can clearly see in a B scan image there is above which some artifacts are there. The artifacts can be removed in signal processing also. Even in D scan you can see clear horizontal line in it. Similarly, area scan also we have taken for measurements. These are the results. In area scan also the 50 mm is clearly visible, and then in 100 mm also the B scan image clearly says the depth of the crack. The depth of the crack is around 110 mm instead of 100 mm. It quantifies in 110 mm, 100 instead of 100 mm. This is how it works. Similarly for 150 mm and 100 mm crack depth. What we inferred from this investigation is, compared to line scan, area scan is much more better and much more efficient to efficiently measure the crack depth in a reinforced concrete member. Conclusion, shear wave ultrasonic imaging with SAFT effectively measures the crack depth in concrete. When compared to line scan and area scan, area scan is much more better. And then with area scan, we can able to detect crack depth of 50 mm to 100 mm. And then further work also we are going to do it in a real-time specimen. Why we wanted to try it out on real-time specimen is, here we have induced cracks. The crack width will be uniform throughout. Whereas in a real-time structure, the crack tip will have one width. The crack above that, the surface will have one width. If we use this method, whether we can be able to detect in the crack depth in a real-time structure, that is what we are going to try it out.
Thank you, Ramesh Gopal. Any questions? Excellent presentation, and he actually patented some of the strain measurement instrument, sorry. So known for his work. Anyway, any questions quickly? One or two? Yeah, Murali. Yes, sir. Murali, 1 second. Huh?
Can we detect delamination?
Yeah.
Okay.
Regarding the contact, generally you should have a kind of a contact medium between the sample and the sensor, so that you will have an acoustic impedance matching between this specimen and the sensor. So in this case, you don't have any kind of a impedance matching material.
No, not required. Not required.
How you are kind of ensure, because air is kind of a more of like the stress waves, whatever are there, they will be get attenuated when you are kind of passing through the air.
Okay.
So how you are kind of ensuring? Are you going to provide a high energy, or how you are kind of?
This is basically a low energy device only. This is not a high energy device. This is a low energy device only. See, conventionally, generally we do to separate the air. Couplants we will use, like a grease or something like that, conventional ultrasonic, that will prevent the entry of air and other things. Whereas this is a dry point contact. That contact itself will eliminate the intrusion of air in it. Such a way they have designed it.
So it is a point.
It's a point contact.
Exactly.
It's a point contact.
Thank you, Ramesh Gopal. And I think for up to 100 mm, there is a little bit of accuracy required. 100 to 200 is getting a good accuracy. And hope you will be testing the actual scenarios. Thank you once again, Ramesh. Next presenter, Vempad is parametric investigation of bacteria-based self-healing concrete, optimization of biological agents, crack characteristics, and environmental conditions. Over to you.
Yeah, a pleasant good afternoon to everyone, respected dignitaries. I am Mukhya Dhanlakshmi. Instead of my professor, I am going to present this under his guidance. and I'm currently pursuing my BTech final year at KG Reddy College of Engineering and Technology. I might be too younger in front of you all. Okay, now I'm going to
Don't worry, go ahead.
Now I am going to present about the formatric investigation of bacterial-based self-healing concrete. The main thing which we have done, this is our research paper and which was published, and the main objective of our study is that firstly it describes about what kind of bacteria shall we need to use, and another objective is that the crack characteristics, which means how much need to be the crack width and length to be its heal, and third one is the environmental conditions of curing. And these are the three major objectives of our research paper. And the three major bacteria which we have done research are, first one subtilis, and another is Pachyris, and third one is Cohinal. These three are the bacteria which belongs to Bacillus family. And while coming to the introduction part, as we know that the traditional curing methods are too expensive and required skilled labors, which is unsustainable. So here we are obtaining this thing, that self-healing concrete that uses bacteria provides a novel and sustainable solution. So the mechanism is bacteria exist in concrete in dominant spores form. It start reacted when cracks appear, then water and oxygen enters, then which activates the bacteria. So the bacteria consume the nutrients and produce calcium carbonate. These calcium carbonate precipitates inside cracks and fills them naturally by restoring the water. And this will help for water tightening, mechanical strength and durability. So you might have a question that what is the difference between laying the natural concrete and here we are using bacteria inside it. As you heard a name, LECA. LECA means it is an aggregate we are replacing with coarse aggregate. 30% of coarse aggregate is replacing by LECA, which is made up of a clay material. So here the bacterial preparation, bacteria is cultured from soil, and bacteria is isolated from the soil and cultured in laboratories. So this reduces the need for manual repairs, and this bacterial precipitation, firstly the bacteria like as I mentioned that concline, Pachyris and subtilis were grown, and these were isolated from the soil and cultured in the laboratory to protect this bacteria inside of LECA, the harsh concrete material. There we then we encapsulated the using of this LECA, which means we used the LECA pellets 4 to 8 mm for porous ceramic spheres, and it is injected through a vacuum process. These pellets were then coated with a biodegradable polymer to trap spores in it. 30% of, as I mentioned before, 30% of coarse aggregate was replaced with these bacteria. This improves long-term protection, slow nutrition releases, and high survival rate of bacteria. And next, here comes the specimen how we laid. We laid a specimen of 100 into 100 into 100 meters, rectangle blocks, cylinder blocks, and here a 25 mm deep notch was added. And next, the curing condition, we have taken 3 cases. One is completely fully submerged, and another is wet dry cycle, and third one is that high relative humidity. And after that, we have gone monitoring and testing session. We have tested it water permeability test and compressive strength. So we have also done visual monitoring. Crack healing was monitored using a portable optical microscope, and crack closures were measured using image analysis software. And water permeability test was done. This test was carried out in JN2H because we don't have laboratory experiments. And next, we got results that healing efficiency, we got observations, and these are the graphs which you can see here. And these are the difference between 3 bacterial graphs and healing efficiency. You might have seen that cracks which we have developed there, and these are the images and the healing efficiency that observation for it develops CaCO3 itself by 28 days. For full water immersion, 0.4 mm cracks closure almost 100% in 28 days, and in wet dry cycles achieved up to 90% crack closures. At high rise relativity, it's only fine cracks, it's all good healing. And the control was 0.3 mm crack reduces only 0.1 mm. And this the side environmental effects, the moisture availability factor is completely healing. Without water, bacteria cannot function. So, for 30 degrees Celsius showed maximum CaCO3 precipitation. For 15 degrees Celsius showed bacterial activity significance. All bacteria worked well in typical condition between 20 to 30 degrees Celsius. And through this, I'll conclude that. And before going to conclude, you can see the difference through the bar graph images. And this is before healing and after healing images of bacterial concrete. And my conclusion is that the optimal system in bacillus spores at 10 to the power 7 CFU ml. These ensclaped in LECLECA, cracks up to 1 mm were healed, and water permeability reduced up to 98%, strength recovered reached up to 90%. Through this, I'll conclude that microbially induced calcium carbonate precipitation significantly improves the durability, sustainability, and service. As I have further, okay, I'll conclude with this, but a small thing is that I have zero knowledge about research. Recently, we have learned pursuing course about research essentials for undergraduate. This is our first presentation. If might be have mistakes, please forgive me. I'll further improve that, sir.
You have presented like a pro, okay? But anyway, good presentation, and congratulations
Thank you,
for
sir.
a good presentation. Any questions? Don't want to trouble? Or, okay, yeah. Yeah. While casting the sample, have you taken any precautions? Because it is a bacteria related.
Sir, actually, this experiment is not completely carried out in our college. We took help from JNTU laboratories for bacterial
specific
growth.
to the question. Have you taken any
Yeah, sir.
precautions?
While casting, we took precautions.
Okay.
But experiment is completely not laid in our laboratory.
No, whatever it may be, have you taken any precautions? Yes or no?
Yes, sir.
Okay, thank you.
Thank you.
Next presenter, Tanveer, SHM of a laboratory model, RCC bridge girder subjected to increasing cyclic loading based on experimentally extracted dynamic responses adopting ambient vibration techniques. Title is big. Where is the presenter? Not there, huh? Check. Naya, no? Okay. Okay, that's it. I think 6 presenters presented, plus 1 keynote address. Thank you audience for the session, and we'll break for lunch.
Unfortunately, no one is there to illustrate. Yeah. అంటే అక్కడికి స్పెసిఫిక్ ఈ సెషన్లో అట్లీస్ట్ Which one?
This is before lunch, no?
This is after lunch, right? It will start around 3 p.m. Yeah, it's delayed. Yes, you have to give. The next session, people, anyone is here, just hand over your PPTs to them. Okay, sure. Sure. ఆ తర్వాత వేసి ఓకే షీట్ మీద
See, participants, any presentations are there? Those who are going to present, please copy your presentations here. అది భయ్యా ఒకసారి
is obtained from the wet milling of the corn, and nutrient broth is used. Nutrient broth is essential for the culturing the bacteria, as without the nutrient broth, the bacteria will not get its nutrients and will not precipitate calcium carbonate. And these were the properties of ordinary Portland cement that we have used for the casting. These are the designation of the mixes. We have prepared the 5 mixes. In different mixes, we have used the different types of water. For example, in TT specimens, we have casted and cured the samples in tap water only. And in TS specimen, samples were cast in tap water and cured in sewage effluent. In SS specimens were cast in sewage effluent and cured in the sewage effluent. And NSB specimens, in this specimens were cast and cured in NB, where NB medium prepared was used by preparing it in the sewage effluent. That is, the water we have used for preparing the NB medium was a sewage effluent water. And last is CSB specimen, where we have cast and cured the specimens in corn strip liquor, and we use the sewage effluent for the preparation of CSL media. This is the pictorial representation of the making of concrete samples, and in the second figure we can see that the bacterial plate and the nutrient broth. By incorporating the bacteria from the bacterial plate, we harvest it in the nutrient broth, and after this we will use this in the concrete. Results and discussions: we have checked the compressive strength of the concrete, and the key observation was that increase in the strength was observed in first 3 days, and maximum 3 days strength was achieved. And in CSB and NSB specimens, because in these we have used the corn strip liquor and NB, and it is beneficial for the bacterial activity. And second study, we have done the half cell potential values to study the corrosion properties. In this study, it was found that the higher corrosion risk was observed in the SS specimens, where the specimens were cast and cured in the sewage water. And the delay in corrosion was noticed in the NSB specimens because of the bacterial activity. The delay is of 14 days, that the corrosion started in the NSB specimens after 14 days. And in SS specimens, it has started at around 4 days. These are the micro characterization properties of concrete, and in this figure we can see the same image clearly showing the calcium carbonate precipitation, and these images were taken from the mix at 28 days of curing, and in SAM EDS sample of SS specimens were also measured, but in this calcium carbonate quantity was very low. These are the SAM images of CSB specimens. In this, CC refers to the calcium carbonate and BC refers to the bacterial cells. And in second image, we can see that the lumps of the calcium carbonate were precipitated on the cell wall of the bacteria. This picture confirms that the calcium carbonate synthesized is of the bacterial origin, and it will lead to the pore refinement of concrete, and it will increase the properties of the concrete. In conclusion, it has been found that a noticeable improvement in the compressive strength was observed in the NSB specimens and CSB specimens. And in sewage effluent SS samples, corrosion takes place after 6 days of microbial concrete, and in NSB specimens and CSB specimens, corrosion was delayed by 14 days and 10 days respectively. This is due to the pore refinement of the concrete and by the EPS layer. EPS stands for the extracellular polymeric substances that the bacteria creates during the bacterial activity, and these EPS layers were observed on the reinforcement bar. This creates a passive layer on the reinforcement, so because of that reason there was a delay in the corrosion, because the disintegration of passive layer takes time. And the SAM analysis confirmed the presence of calcium carbonate in all the bacterial specimens. Thank you for your attention.
Thank you very much. So now we can have a question. Okay. I can take a chance if there is no question.
Okay.
So you are using sewage effluent.
Yes, sir.
If I understand correctly, through the process of coagulation, we add aluminum sulfate as a
yes,
coagulant.
Sir. Yes, sir.
Generally, the effluent consists of sulfate source, and the last process, disinfections, generally we use chlorine. Either it's not drinking water is okay, we won't add. So chlorine and sulfates are there.
Yes, sir.
How can we use in concrete?
Sir, we have checked some of the properties, and like the study was focused on the properties like heavy metals, and these were in the permissible limits. So because chlorides and sulfates, there are other solutions also. The main objective of this study was to use that water and save the clean water for the purpose of concrete. That's why.
Okay. Anyway, I appreciate it's a usage of effluent as well as self-concrete, healing concrete.
Yes, sir.
That's a very
there are various studies that they have used the sewage effluent in the concrete, but we are using this in the bacterial concrete.
Okay.
There are no, I think, 1 or 2 study in that topic also.
Okay. Thank you very much. Yes.
Sewage water, allowing the positive bacteria. There are other bacteria is there, na? A lot of other bacteria also must be there.
Yeah, sir.
What is the? It has no impact on this one.
Yes, sir. It can have the impact.
E. coli, there are so many bacteria, na?
Yes, sir. Yes.
E. coli, there are so many. They have no impact on the concrete.
No, it will have impact, sir. But we are focused on the mechanical properties, so that's why we have checked.
No, they won't precipitate.
No, sir. Only bacillus genes that we have taken precipitates the calcium carbonate.
Others won't.
Others would not.
Okay. Thank you.
Thank you, sir.
So, okay. Thank you very much. Now we can go for next talk. Tejas, please come. So he is going to present about agro-waste blended concrete and with alkali activated combinations and also acid resistance. Over to you.
Thank you, sir. So am I audible? I'm audible, right? Yeah, thank you. So good afternoon all. I'm Tejas, research scholar from IIT Bhubaneswar, and I work with Professor Dinakar Pasla. And I basically work on this development and performance evaluation of sustainable concretes, and it's part of my research work. So the main title is the utilization of sugarcane bagasse ash to enhance the acid resistance of alkali activated slag concretes. So this is the outline of the presentation, and this is how it goes with introduction, objectives and methodology, and concluded by results. And the motivation is like, yeah, we know there's a rapid increase in the population, as a result of which there's a demand for infrastructure also, and we see most of their infrastructure demands concrete, because concrete is widely being used, and the main thing inside the concrete is, the main ingredients which goes into concrete is aggregates. It's consisted of 60 to 70%, and currently they're using cement or LC3 cements. All these things are taking place. But again, what do we do when everything is exhausted, especially the aggregates and your cement also, because cement is the main contributor for our carbon dioxide emissions. So what I thought was, we have new technologies, or they're using all these SCMs and all, but some studies suggest that even though we do a maximum replacement of cement by using the SCMs, max to max we can go with like 10 to 20% or even 30% reduction in the carbon dioxide emissions. So the idea is, what if we completely replace this cement with alkali activated binders or alkali activation technology, followed by by replacing the aggregates with construction and demolition wastes or recycled aggregates. So that's how this concept came out, where we'll be using aluminosilicate rich precursor materials such as GGBS or fly ash or agricultural waste ash, which are high in amorphous silica, and alkaline solutions which are capable of supplying alkali metal cations, so that it helps in the dissociation of the solid precursors. And again, since agricultural waste ashes such as rice husk ash and sugarcane bagasse ash, they are also rich in amorphous content and also amorphous silica, we can try that also. And the other reason is like proximity in the availability, and it's locally available, and that's why we can explore this agricultural waste ash also. Otherwise, and if you see these two graphs in and around, we have the distribution of the agricultural waste processing plants across India, and also we have good amount of C&D waste also being generated across our country. So this is how a brief procedure how we end up with sugarcane bagasse ash. And this is the procedure for GGBS, like we get the blast furnace slag, which is being again grounded to the required size, and we get our GGBS. Since we are using this GGBS in a higher quantity, so we call it as alkali activated concretes. And this is the coarse recycled aggregates which we are using, and we are using two fractions of the aggregate, that is 10 mm and 20 mm downsize. And the basic idea was, we can completely eliminate this OPC manufacturing if we go with this particular technology by using the GGBS as a byproduct, and also this rice husk ash or sugarcane bagasse ash, like it will be openly open disposal can also be avoided if we try to again replace it back into our concrete. The same was the case with C&D waste management, which otherwise would go into the landfills. So we can use this also as a replacement for our aggregates. So the idea was like to use total 100% replacement of these recycled coarse aggregates instead of partially replacing it. But I'll just tell that. So hence, we'll be able to develop a sustainable product which helps in the circular economy. And the objective of the present study was like we are trying to combine two technologies, that is alkali activation technology and also recycled aggregate concrete technology to enhance the properties of this alkali activated concrete and get a sustainable concretes. So in the work which I'm presenting here, we are trying to enhance the resistance of this alkali activated concretes to its acidic environments by replacing it partially with sugarcane bagasse ash, and we have reported compressive strength and acid attack test. And coming to the methodology, yeah, we are using slag GGBS and sugarcane bagasse ash, which has having the following oxide compositions, and two fractions of recycled coarse aggregates, that is 20 mm and 10 mm, and we are using the combined grading suggested by DIN 1045 to get the aggregate proportions, and we are using natural fine aggregates, but the aggregates are natural fine aggregates, yeah. And these are the industrial grade sodium silicate we are using, and sodium hydroxide also we are using, where we are dissolving these pellets in potable water to get 12 molar NaOH solution, and we are using it in the combination of 1.5 ratio and using those as alkaline activator. And this is the mix design which we have adopted. So what we are trying to do is here is like what happens if we vary the alkaline activator to precursor ratio, how the strength and acid resistance influences, and what happens when we again replace it with 10 GGBS, replace GGBS with sugarcane bagasse ash, what happens to the strength and also the its resistance to acid attack. So for this test, we are using this type of rectangular specimens, and we are exposing it to 3% H2SO solution for a period of 6 months. And this test, we have started it after an exposure of these specimens to ambient curing temperature till 56 days. And coming to the results, if we see the results, yeah, you can see here in the red bars corresponds to the compressive strength, 28-day compressive strength. And by using this 100% GGBS as the binder, we are ending up with strength somewhere close to 85 MPa after 28 days of curing, whereas there is some drop in the compressive strength when we are using the second mix, that is when we are replacing it with 10% sugarcane bagasse ash. So there is obviously some drop in the compressive strength. So maybe this is mainly because of the higher presence of CaO content and MgO content which is present in the GGBS, whereas it helps in promotes the formation of hydrothalcite phases and also enhances the reaction components. But when we see the weight loss results, the percentage weight loss is coming down when we are using this 10% sugarcane bagasse ash mixes. Like it's considerably coming down. And also one trend what we can observe is this percentage weight loss is increasing with an increase in alkaline activator to precursor ratio in both the cases. But when we compare with two different mixes, obviously substituting it with 10% sugarcane bagasse ash is helping us. Like it is helping the when we expose it to acid attack, it's helping to enhance the acid resistance. And this, again, we might say that this is mainly because of the amorphous content which is present in the sugarcane bagasse ash, which helps in the enhancement of the acid resistance. And the second thing what we had done was we had checked what was the loss in compressive strength. The figure in the left shows the 28-day actual compressive strength, and the figure in the middle shows the residual compressive strength which we had found after exposing these specimens to acid attack for a period of 6 months. And again, we can see there is almost the loss in compressive strength is almost getting reduced to half when we compare to the 100% GGBS mixes. So again, substituting sugarcane bagasse ash with this GGBS is helping us in enhancement of the strength loss. So though there is the strength loss is somewhere close to 50% in case of GGBS mixes when we go with 0.8 ratio, it is almost getting reduced to 30%, that is almost half. The strength loss is coming down to half when we are substituting with this with 10% SBA. So the key takeaway is that when we are going to use this 100% alkali activated concrete or using a binder, GGBS as the binder, obviously we can see the strength will be on a higher side, but that can be to some extent it's almost still a variation of 5 to 10 MPa will be there, but when we use sugarcane bagasse ash in 10%, what we have observed is we have observed a remarkable improvement in the durability properties, especially the acid resistance, and again acid resistance we have, and also we have seen that there is a decrease in the shrinkage also, whereas I have not reported these results here. So that is what the key takeaway here. The thing was, we are seeing good enhancement in the acid resistance also, acid and durability, other durability properties also. So this is mainly because of, and the other thing is because of the presence of more volume of permeable voids in case of 100% GGBS concrete. So acid finds a lot more spaces, and more amount of reaction products are being exposed for its degradation, whereas in the second mix where we used 10% GGBS, that was not the case. And this can also be one of the reasons for improvement in the acid resistance of these concretes, or even the durability properties. Coming to the conclusion, yes, by varying the alkaline activator to precursor ratio, again we can see some increase or decrease in the resistance, even the strength also, and based on the design requirements of in the site conditions, you can use whatever acid, alkaline activator to precursor ratio is required. And similarly, the replacing it with 10% GBS with SBA is giving good results in terms of durability properties. And also mechanism of improvement is sugarcane bagasse ash contributes in the additional siliceous or aluminum phases, and also amorphous phases, which results in the more cross-linked aluminum silicate gel precursors, etc. So we can, based on the site requirements, we can optimize whatever strength we want, and we can design this particular concretes by substituting 10% SBA in that, so that it takes care of the durability aspects. And these are some of the references which I have used for this work. And thank you.
Thank you very much. I think I don't have any work here. All are completing on time. Yes. Anyway, thank you very much for maintaining time.
Thank you, sir.
And these are very good presentations. You have a 100% replacement, and you are using locally available material.
Yes, sir.
Agro waste.
Yes, sir.
So that is really interesting to see here.
Thank you.
Any question?
Yeah, it's a nice presentation.
Thank you.
See, what molarity you had maintained for that 100% GGBS?
It's 12 molar.
12 molarity. Yes. Sodium silicate to sodium hydroxide ratio?
It's 1.5.
1.5?
Yes.
Okay. So why you are taken 10% as this sugarcane bagasse ash?
Sir,
you can go with beyond up to 30% is also, it will contribute or enhance the strength if you add or if you mix with that GGBS.
Sir, actually what we tried was, when we are using 100% GGBS, obviously we'll end up with a lower strength when we are substituting sugarcane bagasse ash. But in one of our preliminary studies, what we had seen was, I tried to replace sugarcane bagasse ash in 5, 10, 15, 20%. So that time my aim was to achieve higher strength. So using 10% of sugarcane bagasse ash, we achieved strength more than when we use 5 and the other percentages, 15, 20. So that's why I stuck with this 10%.
But if you take 100% GGBS,
yes,
if you go for 12 molar, obviously you will get very good strength.
Yes.
But the main thing is that the durability, obviously there will be the reduction in durability because of the high calcium content in that GGBS there.
Yeah, I agree that.
Yeah. But you can lower the molarity and you can enhance your strength. You done for oven curing or only for ambient condition?
Ambient curing. There's no oven curing.
Okay. Thank you.
Thank you. Yeah, fresh state properties. Yeah, I agree. There is some issue with the fresh state properties. Like we end up with 50, 60 mm slump, and when we are substituting with 10% SB, again we are the workability is coming down. But the thing what we have observed is the setting time is getting enhanced when we are substituting the sugarcane bagasse ash compared to that 100% GGBS mix. Maybe 35 to 40 minutes we are finding with 100% GGBS. When we are using this 10% SBA, it somewhere goes down to 60 to 70 minutes.
Any other question?
Yeah, shrinkage is on a higher side, somewhere close to 900 to 1000 microns we are finding shrinkage, but when we are substituting this with 10% SBA, that shrinkage is coming down.
And what about this, like when you kind of export it for a longer time, there is a high content of sodium inside in the mix.
Yes.
So it's going to kind of form of sodium hydroxide.
Yeah, we are finding some amount of leaching in 100% GGBS mixes, but that is also getting controlled when we are substituting with this thing. Yeah.
Okay, I have one question.
Sir.
So, are you using directly bagasse ash because it consists of lot of fibrous content?
No, sir. We are processing it, sir. Like, yeah, this we have procured this from local from Orissa.
Okay.
Yeah. So the thing is, they are using already 850 degrees Celsius in their boilers.
Okay.
So what we have done is, once we have got the bagasse ash, we are putting it in oven for 24 hours, and to remove all the moisture, and then sieving it with 300 micron sieve.
Okay.
So after sieving, again we are putting it for grinding for some time, and then using it, sir.
Okay, it means that you are removing this fibrous particles.
Fibrous content, yes, sir.
Through sieving.
Yes, sir.
Then grind to
Grinding
cement
it.
fineness.
Yes, sir.
Or slag fineness.
No, just for like 2 hours we are grinding, sir. That's all, not more than that. Yeah.
Thank you.
Sir.
Is it from basic oxygen furnace or from steel furnace? Okay, no, this product which you are using.
Yeah.
Is out of this. This is a byproduct of which furnace?
Sir, actually this talk for next talk.
Title of the next talk.
Yes, sir. Sugarcane bagasse ash. Sugarcane bagasse ash. Yes. Sir, that have not checked, sir. Yes. Yeah, I know. Yes, sir.
Yes. Generally, it consists of around 70.
70%.
70%.
I'll check that, sir.
Yes, you can.
Thank you, sir.
Yes, it's a nice presentation.
Thank you, sir.
Now we can move to the next presentation. So many questions when you are using slag as a binder. So next person, clever, he moved to aggregate. So let's check the next presentation. Yeah, it's over to you.
Yeah. Good afternoon. I am Ganesh Kumar, working in the Research and Development Division of the L&T Constructions. Today I am here to present on performance assessment of concrete incorporating naturally weathered steel slag coarse aggregate in the concrete. Flow of my presentation will be like availability of steel slag in India. Then we will see like what are the issues, why it is not picking up in the market, since we have like coming to the manufactured aggregates, we have limited alternatives for the virgin or the natural aggregates, then few pre-treatment methods, and then results and discussion we'll see. As we already are aware, India is the second largest producer of the steel, and we have around 19 million tons of steel slag waste as on date that is liberated annually, and is estimated to increase to almost 60 million tons by 2030. So we are going to end up with a lot of steel slag waste in the industry, and presently it is just going into the landfills. So there was no meaningful utilization of this end product of the steel waste into the concrete. So based on the usage of the furnaces, the steel waste is broadly divided into 3 types. The first one is basic oxygen furnace slag, the second one will be electrical arc furnace slag, and third one will be ladle furnace steel slags. Based on the basicity ratio, the ratio between the basic oxides to the acidic oxides, it is differentiated between basic oxygen and the electric furnace slags. The basic oxygen slags will be having a higher basicity ratio, which is nothing but like they will be volumetrically unstable, whereas electrical furnace slags will be having the lower basicity ratio, somewhere in a range between 1.5 to 1.8. So they will be better in volume stability when compared to the basic oxygen furnace slags. But as we see in India, like 70% of the steel generation is from the basic oxygen furnace. So we get a lot of basic oxygen furnace steel slag aggregate as the waste material. So every ton of crude that is produced using the basic oxygen furnace liberates around 100 to 150 kgs of the basic oxygen furnace steel slag aggregates. So presently there are many market available products, but they are just landing up in the landfills. So we have taken up this study in order to see whether they can be incorporated as coarse aggregates as a replacement to the virgin aggregates in our concrete. The basic issues with the steel slag aggregates are they are rich in CaO and MgO. But during their process, some of the calcium oxide and magnesium oxide reacts with the other metal oxides and forms a solid material which ceases their hydration activity. But a certain extent of calcium oxide or the magnesium oxide itself will be present as a free CaO and free MgO in the steel slag aggregates. What does this do? The free CaO or MgO, in terms of CaO, it reacts with the water to form CaOH twice, then it reacts with our carbon dioxide to form CaCO3, and they expand over a period of hydration time. The magnesium also does the same thing, forming the magnesium carbonate, but it does in a highly basic, it is not more favorable in highly alkalinic in nature. So whatever the early age volumetric instability that will occur in the steel slag aggregates, 70 to 80% is because of the presence of the free lime, which need to be addressed prior to incorporating in the concrete. Already our 383 standard allows us to use around 25% in case of plain cement concretes, but it doesn't specify anything regarding the pre-treatment. An unpretreated or an untreated steel slag aggregate, when incorporated in a concrete, even at a lower dosage levels, will cause a severe volumetric expansion and causing even as early as 56 to 90 days. So before using these steel slags, so there need to be some certain pre-treatments that need to be done. So the common available treatments are the natural aging or the natural weathering process. And the second one is an accelerated carbonation, which is just picking up in the research nowadays. So in this study, I have taken the naturally weathered steel slag aggregates. So we have gotten these aggregates from a source, from a manufacturer in Orissa. So the aggregates were there in their land disposal yard for 4 years. Even upon reaching our campus, we have kept them for 1 year. And we have studied a freshly prepared concrete using this steel slag aggregate. And within 56 days, we can see even cracking on a small surface structure like 150 cube. So in this, the major advantages with the natural weathering is it consumes the free CaO and MgO to a certain extent, but there will be some free CaO present even in the natural curing of natural weathering after a certain time. So it is a low cost process, but it requires a huge space and it is a time consuming. The accelerated carbonation in a steel slag is picking up now, like it captures the CO2. We can incorporate some CO2 into the aggregates itself, and we can make a carbon negative concrete. So that is where now I'm presently working on. So what does it do? Like we take a certain sample of aggregates and put it in a carbonation chamber and try to incorporate a certain amount of CO2 into the aggregates and use those aggregates in order to make the concrete. The free lime which is present will be converted into calcium carbonate, which ceases the hydration activity upon incorporating in it. But in this talk, we'll see about the naturally weathered aggregates. So these are the basic physical and mechanical properties of the naturally weathered aggregates, which were naturally weathered for a period of 5 years. And we can see like the specific gravity and water absorption were higher when compared to the virgin granite or the basalt aggregates. So the one thing is it had high specific gravity as well as the high water absorption. Like usually in a virgin aggregates, it will be in an inverse order. Why? Because it's like during the cooling process, a certain amount of pores are created inside the steel slag aggregates, and we need to ascertain whether they are interconnected pores or isolated pores. All other properties, the mechanical properties, impact, abrasion, crushing are slightly better when you compare with many sources of granite aggregates that are present in India. Further manufactured aggregates, in our IS 383, we have a certain limitations that need to be met, either in terms of the chemical composition or in terms of the total chloride present from the aggregates, and the source of aggregates that we have received are meeting the 383 requirements. So the thing is, like these aggregates have around 32% of CaO, and the code limits are max to a cap of around 45%. So we have found out the free lime content of the natural weathering. So the initial free lime content that we have done using the XRD was around 2.4, and upon 5 years of natural weathering, it has reduced to 0.8%. So there was a significant drop of around 67% of free lime with the passage of time using the natural weathering. In addition to these tests, like the steel slag aggregates comes with two issues. The first thing is the iron unsoundness or the formation of tufa. The second thing is the volumetric instability. So the aggregates that have been used in this study were even verified those properties. So what happens is when we are waiting, like when we have disposed the aggregates upon passage of some 6 months, like we have identified a small, on the left image you can see a small rust sort of a thing over the aggregate. So it happens like when the iron oxide inside the aggregates is more than 3%, and when it reacts with water and sulfur content is 1% or more, then the steel slag aggregate shows the iron unsoundness. So there were some certain testing criteria where you need to test the aggregates for the iron unsoundness, and we have done the test, and we have found like the rusting mark is not causing any iron unsoundness. The aggregates that we have conducted in this study is free of iron unsoundness. And there is one more test, like you need to alternatively wet and dry the aggregate, so that if there is an excess lime, when we are in the wet stage, it converts to the calcium hydroxide, and during the Dry stage, it reacts with the atmospheric CO2 to form the calcium, CaCO3, calcium carbonate, which forms as a white layer over the surface of the aggregate. Even if the formation of tufa is there, our ministry, MORT, doesn't allow such steel slag aggregates to be used even for the road constructions. So the aggregates have passed both the tests that whatever we have used in this study. There was no iron unsoundness as well as the formation of the tufa. Then we have done the volumetric expansion ratio for the steel slag aggregates as per our 383 Codal standard specifications. The aggregates needs to be crushed to a certain specification, CU specifications, and a sample need to be prepared at the OMC of those aggregates, and under the accelerated conditions we need to conduct 10 cycles, and at the end of the cycle, 10th cycle, the volumetric expansion ratio of the aggregate should not be more than 2% to be used in the concrete. The aggregates were showing 0.96. There was a significant increment from 0th cycle to the 2nd cycle, and post the 5th to the 6th cycle, they have stabilized. So the volumetric expansion ratio was well within the standard limits of 2%. So all these results has motivated us to conduct the concrete trials. So what we have done, we have conducted 12 concrete trials at 4 different replacement levels from 0 to 100 at every 25% incremental levels. All the trials were conducted at a single water to cementitious ratio of 0.35 to not to consider any deviation in water to cement, but we have done at different SCM levels to see whether durability will be improved with incorporating the steel slag aggregate to a higher extent with incorporating the SCMs. The first thing is the fresh state properties, where we have discussed only about the slump. The slump of the concrete has not varied much with the increment level. Even up to 100% extent, the slump of the concrete was not affected with incorporation of the steel slag aggregate. So they are not playing major role either in the initial slump or even I haven't discussed here the workable time. So we have capped like when the concrete will reach a 100 mm slump. So all the mixes perform similar even in the workable time. Then in the mechanical, we have done only the compressive strength because the limitation, the quantity of aggregate is limited to us. So we have done the compressive strength from 1 day to the 28 day. So irrespective of age of the concrete, the steel slag aggregate performed at par. The control mixes, which are with the virgin granite source of aggregates, as well as the 100% steel slag mixes, has given the better results when compared to 25% or the 50%, because the heterogeneity has caused an decrement in strength to an extent of 6 to 8% when you compare with the more homogeneous mixes. So we have designed it for around M40 grade of concrete. All the design mixes, either with incorporating the SCMs or with only the cementitious, has reached the things. Then we have concentrated on 3 durability parameters: water absorption, water permeation, and the rapid chloride penetration. The water absorption will give us an idea about the porous nature of the aggregate that is incorporated. The water penetration will give us whether the pores are interconnected so that there will be a passage of water from with the pressure, then the resistance to the chloride ions. So as you can see in this slide, with the increment in the aggregate level from at the every increment level, the water absorption value is kept on increasing, because as I have already discussed, the aggregates will are having higher pores. So due to the presence of the more number of pores, the water absorption has increased. So if if you want, I'll conclude just a minute. So we are limiting it to only 25% because those are only comparable with the other things. So moving to RCPT, the same way, the initial mixes are at a low, then with the 100% the increment is there. This is how a same image looks. There will be a lot of voids on the surface, but we cannot see with the eye. Due to the presence of the voids and the interconnectivity, the durability is taking a toll when you incorporate at a higher extent. So conclusions of my study, the major conclusion is up to 25% it can be replaced even in the RCC, and we can, instead of going for a plain concrete, plain cement mixes, you need to go with an higher volume replacement of SCMs to cater the sustainability as well as the durability. So that's it. Thank you.
Thank you very much. So now we can have 1 or 2 questions.
Yeah.
Like how you are maintaining the shape of the aggregates, like is it like a circular or it is a random?
No, after the formation there will be like a boulders, then we can crush it to our crushing, like will be similar to our normal aggregate crushing only.
Okay. Is it not going to impact the microstructure of these aggregates that you are developing?
No, microstructure will not be impacted, so we'll be crushing it to the sizes that we desire. We have we have taken a well graded. We have not taken a single grade. Yeah, I have. Yeah. No, I have shown impact abrasion crushing also in my slides. The last three.
Coming to the durability, you had already the slag, you had certain amount of
Hmm.
So
Hmm.
if you immerse in your sulfuric acid or some other acids, obviously it will lead to the huge amount of the mass loss.
No, that acidic immersion we haven't done yet. Yeah. They are promoting for 100% replacement. Even they are, yes sir, they are telling like their conclusion was like it can be used even at 100%. They have a different valorization technique, which is a patented technique. They are even promoting 100% even in the cement concrete roads also, not only in the bituminous.
Yeah. So can you please go to the slide where you have shown the workability with the different thing.
Yes.
So you're showing that the workability increases with increase in the SSA replacement.
No, almost all are same, right?
If you see the columns are increasing, I mean.
No, like the first one is OPC, then there was OPC plus flash.
Yeah, so 0% and 100%, if you see the blue column, column keeps on increasing, right from 0 till 100.
Which one? The blue one, right?
If you compare all the blue ones,
they
are increasing from 0 to 100%.
It is a slight marginal increase that we even see with the normal, there will be a plus or minus 10 to 15 MPa slump.
Okay.
The same thing we have observed.
Can you go ahead to the strength?
Strength.
The
28 day, yeah.
So in 28 day again you are saying that 100% you are getting higher strength.
Yeah, there will be no problem with the strength of this thing.
Yeah, so my question is why you are saying 25% is the limit?
Because of durability, right? If you see the RCPT values, my control mix is having around 650 coulombs, whereas my 100% mix is having around 3000 coulombs.
Now, my question is why the RCPT value is reducing and the strength is increasing? I have never seen this kind of correlation where strength increases but RCPT value reduces.
No, like...
there is something different that has happened here.
Yes. See, the strength of the concrete is not directly proportional to the durability. Higher the grade of concrete doesn't always imply that higher grade concrete is durable.
So what is that? I'm just trying to find out what is that in this case.
See, the IT is a zone which is getting densified due to the presence of a rough texture of the steel slag aggregates. When I'm replacing 100% of those things with these things, my strength is not getting any impact. But due to the presence of the voids, when I'm allowing the cubes to undergo any durability, then I am having an issue with the durability.
And there is a possibility the slag aggregates may react and make a better ITZ. That is the one probability. And one more thing, I have the similar questions.
Yeah.
Now I am the audience. You go back.
Yeah, which one?
Suppose the answer to his question is durability is the concern.
Yeah.
You end up with 25%. In 25% also, it is performing inferior than OPC.
Yes, but it will be
How can you
inferior.
conclude? That's the question.
Oh.
Because durability you are telling, the question is, even 25 is...
Like we cannot like make it like similar to it. There should be a cap like where we can take some extent of the durability which can be worked it out with other aspects. 0.35. It's a single water binder ratio. Common for all.
Okay, anyway, we have enough questions for these sessions. Yeah, good work always demand more questions. So that's evident. So I appreciate the work. So we can move to the next talk. Yeah, please. So,
Respected delegates and my dear friends, I am Kumar, working as Assistant Executive Engineer in Government of Andhra Pradesh. I recently enrolled as a research scholar in JNTU Kakinada. I am here to present a title on the study of circular economy in the concrete, challenges and opportunity. It is only study, it is not my complete research work. This is the agenda of my presentation. Circular economy, it is a transformative economic model that minimizes the waste, maximizes the reuse or recycling, and promotes the sustainable resource instead of traditional take, make, dispose approach. Actually, circular economy minimizes the waste in construction industry. It reduces the construction and demolition debris by reusing the materials. Cuts the generally in the main problem in this urban areas is the refilling, and by adopting circular economic practices in the construction industries also reduces the landfill in urban development administration, and encourages the use of recycled concrete aggregate and industrial byproducts, and conserves the natural resources like sand and gravel. It also lowers the carbon footprint by reducing the cement demand. And economic and social benefits of the circular economy is saves the material cost, creates new jobs in recycling sector, and builds awareness and stronger commitment through sustainable practices. So the main problem with the concrete is construction industry approximately 39% contributes the global warming greenhouse gases, out of which the only cement industry contributes around 7 to 8% of CO2 emissions as a greenhouse gases, and concrete is the most widely used construction material after water, and it also requires high energy. Around in cement production, around 1450 degree centigrade is required for calcination. All these are the problems with the concrete. Hence, we need to adopt the circular economic practices in the concrete. There are many benefits by adopting the circular economic practice in the concrete, and one among them is the environmental benefits. It reduces the energy use. Recycling concrete aggregates reduces the energy use about 40% and low emissions. And by using the Portland cement with the supplementary cementitious materials, reduce the CO2 release. Life cycle assessments indicated that 10% less energy use and up to 0.4% lower global warming potential. So resource conservation, recycled aggregates replaces natural sand, gravel and stone, reduce the quarrying impacts, conserves finite resources and protects ecosystem while supporting sustainable construction. And circular economic practices also reduce the greenhouse emissions. It reduces around 0.4% of by using recycled concrete aggregates. We can reduce the greenhouse global warming potential about 0.4%, and it also saves the cost around 0.23 euros per meter cube. Around 24 rupees per meter cube of cost can be reduced by adopting the circular economy practices. New revenue streams, recycling and resale of recycled concrete aggregate creates business opportunities in the waste management and eco products, and supports job creation and market diversification. Lower production costs, reduced energy demand and raw material extraction lower the overall expenses. Circular economic practices also conserve the natural resources. Recycled concrete aggregates can be fully substituted natural aggregates like sand, gravel and crushed stone when processed and graded properly. This reduces the dependence on the virgin materials, aligning with the circular economic principles of reuse and recycling. Studies showed that RCA can achieve comparable performance in many applications, especially when combined with the supplementary cementitious materials such as fly ash or slag. Less sand and gravel extraction. By adopting the circular economic practice, we can generally the problem with the extraction of the sand and gravel is the habitat destruction, soil erosion and carbon emissions. By adopting these practices, we can reduce all these things. Conserving natural resources ensures the long-term availability of these natural resources for the future generations. That's why we need to we are trying to adapt the circular economic practices in our construction industry. Economic benefits, as I already said, that around 24 rupees per meter cube of concrete price will reduce. and new revenue generation. Sale of recycled concrete aggregate and recycled concrete products creates business opportunities in construction and demolition waste management, encourages the entrepreneurship and innovation in eco-friendly building materials, supports job creation in recycling process and supply chain. Lowering the production costs, reduced energy demand and raw material extraction lower the overall expenses. Recycling minimizes the disposal cost and landfill fees, makes circular concrete economically competitive with the traditional concrete while also reducing environmental impact. Job creation. Expansion of recycling facilities for construction and demolition waste creates a new industrial sector, drives the investment in eco-friendly technologies and strengthens the green economy. Skilled workforce, need for the trained professionals in the material processing, quality control and sustainable construction practices. New business opportunities, development of markets for the recycled concrete products, encourages the entrepreneurship and innovation in sustainable building materials. Open the pathways for the public-private partnership also. Social benefits. Encourage the local participation in recycling and sustainable construction projects, involves the citizens, contractors and policymakers in the shared responsibility for the resource efficiency, builds a stronger ties between the industry and society through collaborative initiatives, promotes education and awareness about the importance of the reuse, recycle and eco-friendly practices, helps the community understanding the long-term value of conserving the resources and reducing the waste. Resilient community. Adapting the circular economic practices, we can reduce remarkably the environmental risk by lowering the waste and protecting natural resources, creates healthier living environment for the future generations, strengthens the community resilience against the climate change, impacts by embedding the sustainability into the local development.
You have 1 minute.
Okay, okay, sir. The main technical challenges in while adapting the circular economic practices is the recycled concrete aggregates often differ in composition depending on the source of demolition waste. Variability in the particle size, impurities and residual cement paste affects the consistency and reliability in concrete mixes. Requires strict quality control and standardized testing procedures to ensure performance. And these practices also utilizes the higher water absorption, and studies already also showed that there is a low strength, around 14% reduction of the strength while using the recycled concrete aggregates. These are the main technical challenges. Apart from that, for adopting these practices in the government, we need to take the policies from the policies and international policy reforms from the government side, and also we need the international collaborations to adopt these practices in the government projects or in society. Actually, there is a concern in the market on low quality aspects of these recycled materials, because we are practicing the traditional practice only. All the people in the industry are not adopting these because there is no guidelines from the government side, and also the research is not reaching to the public. That's why these practices are not adopting in practice.
Can you please conclude?
Okay, sir. Conclusion, circular economic practices reduce the concrete's footprint and conserves the resources, lowers the cost, creates the jobs, builds resilience. The future is technology advances like CO2 curing, new binders will enhance the performances, supportive policies and international standards will accelerate the adoption, collaboration among the government, industries and researchers ensure the scalable and lasting impact. These are the references I made. This is only review, not research. Thank you.
Thank you very much.
Okay, sir.
So we can have 1 or 2 questions. Sir, you can use the mic.
IS 383 has recommended use of recycled aggregates
but still,
to a certain extent.
you
can't say that there are no
even though many IS codes are there to use the different concrete materials, but in government especially, they are not adopting because we...
Adoption is different. You said the standards are not there. IS 383 is recommending use of recycled aggregate.
Okay.
Right?
Yes, sir. We are not practicing because of
ICA has got a document also, public document. Indian Concrete Institute.
yes, so,
one of the main problems of reusable aggregates, there are no crushers, anyone using it, because they find it inconvenient to use it for a small quantity when natural aggregates are already available, and these reusable aggregates, enough research, quite a lot of research has been done, but it has not been still applicable in the real field. If it is available, people will go for it. But as it is uneconomical so far, they are not able to implement it in the real.
Actually, my thought is that...
I think it is not a question, it's a suggestion.
Yes, sir. Yes, sir.
Yes. And we can have one last question. If anyone have question, by considering the time, we can have one more question.
Okay,
Do you want to tell
yes, sir. Actually, in construction industry, it is a very much unorganized sector. If it is organized, if concrete is always, if ensures, if there is a policy, we need to use the RMC only, then we can easily adopt these kind of practices by making, because we need a high level of quality control to adopt these kind of practices. That's why if we move from unorganized to organized, then it is very easy to adapt it.
Thank you very much. Anyway, by considering this session in circular economy, this presentation is like an overview of the session. Thank you very much. So now we can move to the next speaker.
Good afternoon, everyone. I am Saswat Dwivedi from IIT Hyderabad. I am working with Dr. Meenakshi, and I am going to present my research on the topic life cycle assessment of mortar with recycled mixed powder as a supplementary cementitious material. Coming to the presentation outline, I will first introduce my work, followed by the methodology, followed by the LCA, and the results and the conclusion. As we all know that C&D waste is getting generated around globally, that is the quantity of 3 billion tons annually. And generally in countries like India, we are following a wet recycling of these aggregates that is producing waste water from that plant. And this waste water generally contains traces of unhydrated cements and hydrated phases of the cement and fines from the natural aggregate and bricks and tiles. Due to this mixed composition of this waste water sludge, the powder we are getting out of it, we have termed this as a recycled mixed powder, and it has a potential to be a supplementary cementitious material. And by using SCMs in the concrete, we want to reduce the carbon footprint, as this is one of the key strategy. And to quantify how much the sustainability that RMP has, we have conducted a LCA analysis to quantify the environmental sustainability and to identify the hotspot in the supply chain for the further improvements. By doing this, we want to first valorize the C&D wastewater sludge, and we want to use it as a SCM so that the carbon footprint also reduced. This is a general production process for the recycled mixed powder. It starts with the demolition site, followed by the recycling plant, and the plant we are getting that wastewater sludge. As this is a waste from that plant and it has no economic and scientific value at this point of time, the impact coming, environmental impacts coming till this point of the life cycle, we have not considered in the entire life cycle assessment. But the transporting from that wastewater sludge to the lab, then getting it dried and getting it grinding to get the recycled mixed powder, those impacts has been considered in the study. This is my system definition, where I have chosen a cradle to gate approach. Here two stages are there. That is, one is raw material production and the mortar production, and the transportation is also considered. But the maintenance during the service life and the afterlife of that mortar is not considered here. functional unit is in LCA serve as a basic unit for the quantification of the environmental impacts and to compare between two alternatives. So in this case, we have choose three type of functional unit. One is the 1 ton, first one is the 1 ton of motor production. In this case, we have considered the impact coming from the RMP processing, that is the drying and the grinding. In the second case, here also we have chosen 1 ton of motor only, but no allocation from the RMP processing has been considered here in this case. Coming to the case 3, where we have used a performance-based functional unit, and two performance of the motor has been considered. One is the 28 days compressive strength, and one is the charge passed during the RCBT testing. So, one representing the mechanical aspect of the material, and another is the durability aspect. So, by using this coefficient equation, we have quantified the comparative functional unit coefficient for different mixes. Coming to the result section, here the blue one represents the energy consumed when we are considering the impact from the RMP processing, and the grey one is when we are not considering any impact from the RMP processing. So if you see in both cases, there is a continuous reduction in the energy consumption value with replacement of RMP. But if you just compare the 30% RMP mix and the 20% fly ash mix, for the case when no allocation is considered, in that case the 30% RMP mix is showing less energy consumption. But when we are considering the impact coming from the RMP, that is not the case. So there is a need of considering the impact coming from the RMP processing. Coming to the GWP value, here also similar trend has been seen. There is a constant reduction in the GWP. And if you just compare the 30% RMP mix and the 20% fly ash mix, it is giving similar GWP value even after consideration given to the RMP processing stage. This is a sensitivity analysis with respect to the choice of the functional unit for the LCA. And here the blue series represent the 20% RMP mixes, followed by the yellow series is for the 20% RMP mix, and the green one is for the 30% RMP mix, and the 20% fly ash mix is represented in orange color. So here for the energy consumption part, the 10% RMP and the 20% RMP mix, when we are considering the performance-based functional unit, it is showing higher energy consumption than the base OPC motor. But the 30% RMP mix and as well as the fly ash mix, that is showing lower energy consumption as compared to the OPC motor when we are also considering the performance aspect. Coming to the GWP, in this case also 20% RMP mix and 30% RMP mix are giving lower GWP value as compared to the base OPC motor, even after the considering the durability and mechanical performance of the material. So generally in the LCA of the construction materials, we use sustainability indices such as the carbon dioxide intensity and the energy intensity. We try to plot that value as well. Basically these intensities are defined based on the 28 days compressive strength. So in this case, all the mixes with the different SCMs that has a higher CO2 intensity and energy intensity than as compared to the OPC based motor. But among the three RMP based motor, 20% RMP is showing lowest both intensity, CO2 intensity and energy intensity. But when we have, in the previous slide, when we have considered the performance aspect, that is durability and mechanical strength also, in that case 30% RMP mix showed the optimal value. But in this case 20% value is showing the optimal value. So there is a need to consider the durability aspect also in the supplement LCA of the material. Coming to the hotspot identification, here we have plotted the consumption, energy consumption and GWP coming from different stages of the life cycle of the motor production. And as you can see in the 30% RMP mix, that is our optimized mix. So in this case, only from the RMP processing, that is ball milling and drying, that is contributing around 14% towards the energy consumption and 9% towards the total GWP. So as in this study, we have calculated this impact from the RMP processing based on the lab scale machinery operation. So by considering the industrial scale production and those things, maybe the sustainability of the RMP can be further increased. Coming to the conclusion, RMP has a sustainability potential, but the improvement of the performance of this RMP mix could also further increase the sustainability of this material. And 30% RMP mix is showing similar GWP value as compared to the 20% fly ash mix. And as we have discussed the sensitivity analysis with respect to the functional unit, there is a need to decide a framework how we want to compare our different alternatives, different SCMs. So and coming to the consideration to the industrial scale machinery operation, that could possibly change the perception towards the RMP sustainability. Thank you.
Thank you very much. So, any question? So anyway, I take the opportunity when there is no question. So the main purpose, are you replacing OPC?
Yes.
Yes. So the effect when you replace the OPC
Yes.
here, anyway you are using the waste material.
Yes.
So what are the parameters you consider? Because we keep lot of, even OPC we need to grind.
Yes.
We need to preheat.
Yes, yes.
Yes. Why can't you add directly this material in the ball mill?
Yes.
And you can do the
yes,
intergrinding.
because generally that preheating of the OPC production, that is, we are using the heat from the clean to the supplying for the drying end purpose. But in this case, we are using electricity from the in the lab. So if we are can in industrial scale, we can actually process that RMP. Maybe that that will consume less that energy and GWP.
Yes, I have one more question. What is the base? Here you are considering the processing and without considering the processing. Anyway, you are adopting
yes.
processing. So you can go with the processing considerations.
But
what is the
generally
base
in the available literatures for the life cycle assessment of supplementary cementitious material, their assumption is that it is a having zero tag. But that's what I wanted to highlight, because that is not the exact case if you directly consider it as zero GWP and energy consumption.
Very good, very good. So in addition to using the material, so he actually quantify what is the environmental benefit. That is one of the key aspects of this study. Thank you very much. So now we call the next speaker. Yeah, please come. Yeah, you are not. Shah. Mr. Shah.
Good evening, everyone. My name is Robin. I work in ACECON in the Research and Development Department. So the topic of my presentation today is valorization of C&D waste sludge as a high reactive SCMs. So before going into my presentation, a brief introduction about our company. ACECON is one of the pioneer in the industry of tile and stone installation. We provide flooring solutions, 3D mortars, and plastering solutions. We have 9 plants around India, and we also support business units around the globe, except for North America. We have business units in China, in Australia, and Philippines, and we provide technical solutions to those BUs as well. Coming back to my presentation, so the presentation is divided into 3 major contents. The first is why are we doing this study in the first place, followed by the experimental approach, and what are the performance in terms of mechanical and environmental impact. My previous speaker spoke about sludge. It's the same topic, but I want to discuss why sludge is more important in this aspect. So if you ever visit a recycling facility, you will see a pond of fine sediment across the recycling facility. So what are these? These materials are basically the result or the outcome of wet processing of the C&D waste, which is more commonly known as C&D sand or C&D aggregates. So in this study, we wanted to see if this sludge or the waste, wet waste can be utilized in cementitious mix. So for that, and also as per the report of in 2021, India produces around 150 million tons of C&D waste. And out of this, only a few fractions get utilized. So we wanted to see, if a waste of a waste can be utilized in cementitious system. So yeah, given, as I said previously, it is a waste of a waste, definitely it's going to have variability. So to address that, we deliberately collected 3 batches from the same recycling facility. And we wanted to keep the sample preparation as minimal as possible, so that if this system works, the recycling facility could use it at a very lower capex investment. So we first dried it for 50 degrees Celsius for 4 hours, followed by manual disintegration, and we characterize this through particle size distribution, TZ and XRF. And for the testing framework, we did pozzolanic activity index. We also saw the dimension stability, and also the water absorption, and also the life cycle assessment, which the scope is from cradle to grate. So coming with the oxide compositions, you can see all three sludges are different in terms of oxide composition, but if you combine the silica, alumina, and the iron content, it closely resembles to that of class F fly ash composition as mentioned in the ASTM standard of C618. So it is similar to that of class F fly ash, but we cannot ignore the higher alkaline content in it. You can say it's almost thrice than that of OPC. But while casting the specimens and even observing the specimen for more than 50 days, we did not see any sort of leaching and any sort of expansion. So probably these alkalis are bound within the CSH and not present in the pore solution as free ions. Moving on to the next characterization, we did the TZ analysis, and you can see the LOI is huge. It ranges from 12 to 20%, which is indefinitely huge for any natural pozzolans. At this time, we were a bit hesitant to use this in our study because given the higher amount of, given the higher LOI, it could actually hinder with the hydration products. But eventually, we went through this study. And if you see the particle size distribution, it's similar to that of OPC, and there are sufficient fine fractions that can actually, be enough for particle packing and nucleation, if not reactive binder. So yeah, as we assumed, there was batch variability among the specimens, and from our characterization, it's pretty much clear. Moving on to the mechanical performance, we went for pozzolanic activity index at 5 and 10% replacement, and you can see above, in all EASES, it's above 75% criteria set by the ASTM standard. But at this replacement doses, it's mostly particle packing rather than the binder reactivity. So we move forward, we push to 15 and 20%, and here you can see the results are similar. We are meeting the ASTM criteria, and the major two things we can conclude from here is basically the sludge, it's partly reactive, and despite having variability, it meets the ASTM standard criteria. So we were able to go up to the replacement level of 20%. Moving on, after the study of our compression, we moved towards dimension stability, and here we studied a drying shrinkage. And as you can see, all three sludge mixes at 20% replacement has a bit higher shrinkage than that of OPC, but it still meets the ASTM criteria within the limit of 0.03%. And one noticeable thing here, if you could see, is the percentage of mass loss compared to that of percentage shrinkage is a bit high. That is basically the drying is happening in the system, but the microstructure is resilient to the capillary tension that is being formed. So yeah, shrinkage is not a risk for this sort of a mixed design. And the next parameter we studied was basically tell you about the connectivity of pores, for which we did the water absorption. We did it for one particular mix, that is sludge 2, at 20% replacement, and you can see clearly that the early absorptivity is a bit reduced, which indicates that there has been refined, the pore is being refined at the surface, but eventually it picks it, you can see it picks it up, and it is slightly higher than that of OPC. But we can always correct this with the right amount of right chemistry of admixtures or polymers to address this issue. And our previous speaker spoke very in detail about the LCA scope and all. I'll not go into much more detail, but yeah, if we replace at 5%, we'll see around 4% of reduction in CO2, and when we are going up to 20%, we'll see around 17% of reduction in CO2. So in conclusion, yep, we can engineer this CND sludge into low carbon cementitious system, and we can go up to 20% of replacement. And even if it is shrinkage or permeability, it can be, it is within the acceptable blended system limit, but we can always fine tune it with the right admixture chemistry, either superplasticizer or shrinkage admixtures, or even radius plasmal polymers. Yeah, these are the references. Thank you. If you have any questions.
So we can take 1 or 2 questions. Okay. By considering the time, we can move to next scholar if there is no question. So Joseph. So C is going to present on the optimization. So what happened? Is there?
Okay. Good afternoon, everyone. I'm Jyotsna. So I'm from Bijpilani, Hyderabad campus. Today my topic of presentation is recycle of rice husk cash for sustainable concrete production, waste to resource optimization. So before I begin into the presentation, so far till the presentations happened, every presentation has one focus towards the sustainability perspective or utilizing the waste or conserving the environment with the already existing waste. So my presentation is a like in one of the previous presentation, one speaker told about we are not using it. Most of the people are working to the paper end, but when it comes to the actual usage in the real life, it is very like there are many constraints and barriers to use it. So I have so my presentation focuses on how effectively we can take the work from a paper level to the actually application level. So let's begin with the presentation. So we all know this, India is the second largest producer of rice after China, but mostly after the paddy has been extracted for the rice and all, the rice husk and rice straw are mostly commonly disposed of in open fields, and this is very famous in our northwestern states like Punjab. So the problems associated with the field burning is, we all know about air pollution, land pollution and the respiratory disease. But on the other hand, several studies have proven the potential of using rice husk for energy and also as rice husk cash as a supplementary cementitious material. So why can't we, and there exists thousands of literatures on how effective rice husk cash is as a supplementary cementitious material. So the motivation for my study is, even though we know that rice husk cash is a potential supplementary cementitious material, why are we unable to use it? Because we don't have a proper availability and accessibility data and where we can procure these materials and all. So this lack of optimized use of biomass waste in construction is one of the research motivation, and we all need a systematic approach to utilize the SCM. Like we have an approach only for the fly ash, but not for the rice husk cash. So I have taken how can we use this rice husk cash to the RMC plants in one study area. So based on this research motivation, the objectives that I have framed is how can we use the existing supplementary cementitious materials like RHA, SCBA and fly ash for the production of the ternary cement, and for that I have developed a computational optimization model, and I have applied this model to one region in Tamil Nadu. So getting into the methodology, so this is my optimized RHA supply chain for the RMC plants that I have chosen for the study area. So the location of the facilities where we can, where the RHA is available. Then what is the RHA available capacity from that plants that have been taken. Then when we are supplying these RHA to the RMC plants, what is the plant specific demand? Not every cement plant or not every RMC plant will have the same capacity. So we have to go for the plant specific demand, and we also have to check that what is the potential of RHA use in that specific plants. Then the objective has been formulated based on this supply points and the demand estimation. So the main objective is a twofold, where is maximizing the SCM utilization and also minimizing the transportation cost. So cost is usually taken as a per ton per kilometer when we are transporting any material. So I have taken the distance to the plants and cost per ton per kilometer as a parameters in my objective framing. Then what are the supply constraints I have included supply constraint, demand constraints, and also the blending constraints in the objective function. So the supply constraints are supply can never exceed the available material. Demand constraint is demand can never exceed the required demand of a specific RMC plants or a cement plant, and also the blending constraint. Suppose some cases, depending upon the RHA quality and their reactivity, So we can use either 5%, 10%, 20%. It varies from material to material from where we have procured RHA. So the blending constraint parameter has also been involved in the optimization technique. So overall, an equation has been formulated and to maximize the SCM utilization and minimize the transportation costs. So the developed optimization, the developed steady area has 7 supply points and all 8 RMC plants in the steady area. So we have optimized to check from each supply to each demand point to have an optimized flow pattern. So this is a steady area that I have considered in Tamil Nadu, and that steady region has about 8 RMC plants, and the picture represents the location of those RMC plants. So after the optimization has been done successfully, we will get an optimized flow pattern for the distribution of the ashes, and we can see the efficiency patterns for the material utilizations. So if we observe here, for the production of the ternary cement concrete in the 8 RMC plants that are there in the steady area, the SCBA has been completely utilized. And we can still the efficiency of the RHA and FA is very much less, is around 38% and 20%, and still it shows that there is a lot of potential to produce the ternary cement concrete with the existing SCMs. So if we also notice that at higher demands in case of SCBA, we are attaining the stable efficiency, whereas in lower demands, it shows that still there is a lot of potential for us to generate the supplementary cementitious based concrete and use it in the construction sector. So the major comprehensive finding of this optimization model is we will get what material can be procured from what supply point, and it can be sourced to what destination point in terms of quantity we can get it, and also we can have a optimized flow pattern. So if you see the flow pattern, each RMC plant is procuring either fly ash, RHA or SCBA depending upon the optimized pattern by considering the transportation cost and the availability of the material and also the blending ratios that we have given. So after developing this model for a particular steady area, we have scaled up it to the entire state of Tamil Nadu. So this is the state of Tamil Nadu. We have divided each state into certain set of zones, and the figure depicts the rice husk availability and distribution in the Tamil Nadu state. So, and the right side figure shows the distribution of RMC plants in the Tamil Nadu state. So whatever the model we have developed for the small steady area, we have scaled it up for the entire state. So there are about 71 RMC plants in Tamil Nadu state, overall Tamil Nadu state. So if we see the efficiency of the RHA, utilization in the RHA or SCBA and fly ash, here we can see that in most of the RMC plants are found to be beneficial by utilizing the SCBA compared to fly ash. So this is the efficiency chart. The efficiency chart clearly signifies that there is still a lot of potential for us to use the existing rice husk ash in the real life construction sectors like RMC plants in Tamil Nadu state, as the efficiency still lies in around only 28%. So this is the optimized flow pattern. So RMC, so depending on, for example, if the RMC plant capacity that we have considered is suppose 100 meter cube per hour. So if we want to meet 10% of its demand capacity, what is the flow pattern for each material? It means which RMC plant has to procure, the 71 RMC plants, which RMC plant has to procure from which supply point. So the optimized flow patterns for each RMC plant for each varying demand is a major outcome of this optimization model. So here I am just showing few for an example. To meet the 100% demand capacity, it means the available SCM resources in that particular state that I have chosen as a steady area is sufficient enough even to meet 100% demand capacity of the 71 RMC plants, which runs with a capacity of 100 meter cube per hour. So the conclusions, I have confined these conclusions only for the steady area that I have taken. So this computational framework can be scaled up to any other area by making the minor changes in the supply constraints and the blending constraints that we are choosing, and it can also be scaled up to any type of concrete. Here I have chosen ternary cement concrete, but by varying the blending constraints, it can be varied up to binary concrete also, or other supplementary cementitious materials, ternary cement concrete. And also results shows that 90% of the total SCM can be utilized 90% of the total SEM demand can be fulfilled using the existing local resources, and 7 out of 8 RMC plants have the potential to produce RHAFA based ternary cement concrete, because we have total 8 RMC plants in the study area we have chosen. So 7 plants can produce RHAFA based ternary concrete, whereas 1 RMC plant P8 has a capacity to produce SEBA and RHA based ternary concrete. And this study, unlike the experimental study, this study provides a practical pathway to use the existing resources and existing data and applicable it in the real life construction sector. Thank you.
Thank you, Josna. We can take 1 or 2 questions. Yes.
This rice husk waste which comes out from the fields, it has got one of the advantages is to use it as an insulating material. You have got insulating boards, you have got insulating. Perhaps it can be also used for making bricks as insulating material. It reduces its weight. Now, when you use this rice husk in the RMC plants, what are the disadvantages which will create, or is it having some insulating properties? Because when you're constructing a building, these days you need to see how cool your building is, how it is being insulated from the external heat. So this, by using rice husk, does it have this effect?
Sorry, sir. Rice husk ash.
The presentation is, she is not using rice husk, she is using ash.
Rice husk ash.
After burning. Yes.
After.
Yes, you can answer the question.
Sir, actually, rice husk ash, utilization of this rice husk ash as a supplementary cementitious material is proven to be beneficial from the mechanical strength properties, from the mechanical properties and the durability properties. Like several literature has proven that. So I have taken that literature as a base, and that properties whichever the rice husk ash is fulfilling, we can use that rice husk ash in a RMC plants for producing these blended concretes.
No, but my question is, actually rice husk ash has to be burnt at a particular temperature zone only to produce a concrete beneficial product.
Yes, sir.
If it is burned at a higher temperature, it goes in crystalline silicon dioxide.
Yes, sir.
And it is not useful for silicon SEM actually.
Yes, sir.
So is that being burned at that particular temperature zone? That's my question actually.
Yes, I understood. That's why I have mentioned in my introduction slide itself. Yes, sir.
Maybe I missed so many phone
Yes. Yes, sir. We have to send it to the particular cogeneration plant where we have a controlled burning.
Correct.
We cannot do uncontrolled burning to use it. Yes, sir.
Because at 800 degrees of temperature, it goes to crystalline range, and it won't be useful as a
Supplement. Yes. Yes.
Doesn't have ozone effect actually.
Yes, sir. Whatever. No, sir. That's.
No, that's a good point. Actually, already the processing of rice husk ash and properties are well known.
Well, yes, sir.
So your focus is how to access that
How
rice
to
husk.
make it for the industrial acceptance. I'm showing some pathways for that.
That's your scope of the study.
Yes.
Yes. Anyway, it is very interesting to know. We have a lot of studies. We have one final one, which is high volume biomass based studies. Please.
Thank you.
You can come. You can take it.
Hi, I'm Neela Kanmani. I'm a PhD student working with Dr. Piyush Chaunsali and Dr. Manasantanam from BTCM Group, IIT Madras. Today I'm going to present on performance of high volume biomass ash-based binders in acidic conditions. So let's move to the overview of the presentation. First, I'll be presenting the research background followed by motive, objectives, and what are the materials used for this binder formulation, and what is the binder performance in acidic conditions, and followed by conclusions. So first, let's see what is agro-based biomass. I guess the previous speaker would have explained it very clearly what is agro-based biomass and what is agro-based biomass ash. So here we have different sources of biomass, particularly from India, from 5 different sources. Out of it, 3 major sources are from agro-based resources. So we are mainly considering that one. So in India, we have wide availability of biomass, which is used as fuel in industry, which generates as a byproduct, which is rich in reactive silica.
However, we have some challenges in utilizing these ashes in cementitious binders. Mainly the variability in ash composition and the presence of unburned carbon limits its utilization. So mostly it goes to the landfill, which affects the environment, contaminates the food chain and the surrounding environment, and also contaminates the groundwater as well. So we need to find alternative ways to utilize this waste. So now the current research focus also limits the utilization of biomass ash to 30 to 40% in conventional systems, beyond which it affects the performance. So we need to formulate alternative binder formulations which could have high volume utilization. So the objective of this research is to understand the influence of this varying ash composition, because industry mostly a mixed feedstock is used, so we need to understand the influence of this varying ash composition on the reactivity, and we need to formulate high volume ash-based binders with alkali activation, but not with strong alkali activators, because that also limits the utilization. And third is to investigate the stability of these binders at low pH environments. Because we are going to the alkali activation, how does this binders going to work with the alkali binding part? That's the main problem here, so we need to investigate it further. So I have considered two different materials for the binder formulation. One is the silica-rich and alumina-rich ash. We have already studied the reactivity of this material. We found that the alumina-rich siliceous ash has high reactivity compared to the silica-rich siliceous ash, which is already published, so I'm not going to talk about it much, just to have an intro to the material. And moving to binder formulation, I have taken 90% of the ash activated with 10% of lime and 1 molar sodium hydroxide solution cured at 50 degrees Celsius. We are adding alkali solution mainly to increase the pH so that it could facilitate the dissolution of aluminosilicates from the ash. And then we are curing at higher temperature, but I have formulated the binder even at room temperature, but to accelerate the reaction kinetics, we are curing at 50 degrees Celsius. So the powders are dry mixed, then we are adding the alkaline solution, then it's hand compacted, then it's mechanically pressed because it's very difficult to do hand compaction, the efficiency is very low. So we are doing mechanical pressing, then followed by specimen preparation. We'll just neck it out and then take the specimens out of the molds. So the main problem is here we form calcium bearing gel phases. It's calcium silicate hydrate, but it's not CSH as we see in the conventional system, because it has calcium to silica alumina ratio mainly less than 0.6. So below which the structure of toberomite is not stable. It's not stable. So it forms modified gel based phases. So the alkali binding of such calcium bearing modified gel phases is not well understood. So the motive of the study is mainly to understand what is alkali binding performance of these modified gel phases. So now let's move to the results part. So when we study the compressive strength and water absorption, alumina rich has higher strength compared to silica rich ash. Silica rich ash has about 25 megapascal and alumina rich has about 25 megapascal. And when it comes to water absorption also, we were able to see alumina rich has very less water absorption compared to silica rich ash. Why it could happen? When we characterize the binder, we are able to understand that alumina rich ash binder with increased alumina uptake found more ordered reaction products, which increase the strength as well as it decrease the water absorption because of the well densified microstructure. And in silica rich ash binder with lower alumina uptake, it formed more poorly ordered and amorphous reaction product, which decreased the strength of the binder. And we are able to see the nice difference in the microstructure. Silica rich binder formed a more porous microstructure and alumina rich binder formed a densified microstructure, because we could see some starting rate platelets well densified within the gel-based binder, gel-based phases. So now moving to the acid resistance of this binder. So the specimens were immersed, 25 mm cube specimens were immersed in acid for a period of 4 weeks, and the acid was replenished every week. So to measure the change in mass as well as the change in pH. So here we're able to see the strength part, we're able to clearly see that alumina rich binder has shown very good results. But in acid resistance, it was a game-changing phenomenon. It was good for silica rich binder, because silica rich binder showed higher strength. Sorry, the point is not working. If you see the second figure, we are able to see that silica rich binder has shown increase in strength in pH 2, but at pH 0.5, both binders should decrease in strength. So then when we looked at the change in mass, silica rich binder always showed mass gain and less leaching in the acid solution. So which led to form a more intact specimen and good acid resistance. When it comes to alumina rich ash, it has shown more mass loss and more alkali leaching, which led to more distress in the binder. Coming to the alkali binding part, we measured the alkali binding part with the help of apparent pH measurement and efflorescence test. With the apparent pH, we were able to see the pH of alum-rich binder was quite high as compared to silica-rich binder. But the amount of calcium added, the amount of alkali solution were all same. Then why the pH would be higher for alum-rich binder? Because the formation of more ordered reaction products provided less number of reactive sites for alkali binding, which limited the alkali binding part, which also rise to severe efflorescence in alum-rich binder, showed in the second figure. So in a low calcium, low alkali binder system, which eventually mostly forms a calcium bearing modified gel phases, silica-rich binder with a lower alumina uptake and with SiO-Si bond, it has enhanced alkali uptake and retention in alumina-rich binder. It shown poor alkali binding mainly because of the formation of less reactive sites for alkali sorption. So in the summary and conclusion, I want to say silica-rich binder found more porous reaction product, but eventually it formed lower compressive strength. And alumina-rich binder formed more ordered and crystalline reaction product, formed a well-densified microstructure and higher strength. But when it comes to stability of the binder, silica-rich binder took the higher seat. It accommodates more acid-prone reaction products during acid immersion. Also, the SiO-Si bond formation have more affinity for alkali binding, but with SiO-Al bond, it has less affinity for alkali binding. This is only to a low alkali, low calcium binder. When it comes to high calcium, it's entirely different. And we have just tried to propose an outcome. For within the time demand, I don't want to explain in detail, but if you have interested, you can come and talk to me. Yeah, we have tried to propose this framework for utilizing high volume of biomass ash. Thank you.
Thank you. We can take one or two questions. So anyway, attempting biomass with low volume is challenging. The interesting part of your study, attempting biomass with high volume, it's really challenging work, bold attempt, appreciated.
It's not for a cementitious binder, we're mainly aiming at forming a construction product, which is more practically applicable and scalable, not, yeah.
Okay, thank you. There is no more question. By considering the time, we can conclude. I summarize the session. Total, we have 8 presentations in this session and 3 presentations on agro-waste assets. And 1 presentation from steel slag aggregate and 2 from sludge waste. And 1 presentation overview of circular economy. And it is interesting, we have 1 more presentation also from LCA. So by considering circular economy, we have a wide range of exciting presentations. And on behalf of organizing committee, I appreciate and express thanks to all the speakers for maintaining time. And also, we thank the participants for thoughtful questions. Let's conclude these sessions. I hope you enjoy the rest of the sessions. Hope we see to you in the next sessions.
Thank you, Professor Baharuddin. It was a well-handled session, and thanks to all the participants also for maintaining the time limits. Now, so it gives me immense pleasure to welcome Professor Manu Santanam, who came to this session. And I request sir to felicitate Professor Baharuddin and Professor Jagdish Vengala, who were the keynote session chairs for both the sessions today. And I also request Dr. Kantara Garu to be dais. Yes.
Next tea break. Tea break. Just 10 minutes.
The participants are requested to join us for a small tea break, and the next session will start exactly at 5 o'clock. Just 10 minutes, please be back in time. And the next session, participants are requested to upload their PPTs in the desk.
Yeah, industry persons invited talks. You can upload your presentations here. Yes, sir. You can connect laptop connectors. Sir, keep it here.
Yeah.
Yeah.
We'll check once.
Yeah, you can check it, sir. So you also want to check the presentation? Okay. Sir. Yeah.
Okay. I'm ready. my WhatsApp number. Okay, I'll ping you very well. Yes.
I'll ask everyone.
Just one correction. Just one. No issues.
Good evening, everyone. It gives me an immense pleasure to introduce our session chair, Professor Anurag Mishra. Professor Anurag Mishra is a professor of civil engineering and Dean Infrastructure Planning and Management at IIT Jammu. He previously served as CEO of an infrastructure company where he led planning, design, and execution of pre-engineered steel warehousing projects and steel concrete composite elevated roads, and established an advanced automated facility for precast and heavy prefab steel structures. Earlier, he worked in academia as a professor and head of structural engineering and coordinator of the Center for Building Technology and Construction Materials at MNIT Jaipur, and as a director of Anand International College of Engineering, Jaipur. He has also undertaken research and consulting work at Liverpool John Moores University and Curtains Consulting Engineers under a UK-India REC project. His research interests include waste utilization in concrete, durability and repair of concrete, NDT, high volume fly ash concrete, SCC. Thank you. I'm handing the chair to Professor.
Let's save time. So very warm welcome to all of you, and we are going to have this session in continuation of the earlier proceedings going on since yesterday. And the first presentation is going to be delivered by Engineer S. Navanale, Long Span Structures Private Limited, ultra high performance fiber reinforced concrete and efficient solution for sustainable infrastructure. So I invite Indian Navanale to deliver the talk and request. Okay. So you please make the correction, right? So Mr. Sudeep, right? Mr. Sudeep would be delivering this and would request you to finish it in 18 minutes max, right? Thank you so much.
Can we start? Yeah, sure. So I welcome everybody here. So 5 o'clock is evening time is a very difficult time to grab everybody's attention here. So we'll be presenting on ultra high performance fiber reinforced concrete, a game changer technology for ultra durable structures. So basically, just to take you through introduction of UHP FRC, it's basically a cementitious matrix, densified matrix material with the steel/organic fibers. So the contents that we have in UHP FRC is basically cement, microsilica, fine sand, water reducers or admixtures, along with steel fibers and the water in the form of ice. So basically, the key innovations that we have done as compared to conventional concrete is that basically there are no coarse aggregates. So by eliminating weak interfaces, we are achieving much higher strength as well as durability properties. And because of removal of coarse aggregates, and we have also reduced the porosity, so we achieve a micro level dense particle packing, so thus increasing its strength as well as durability properties again. So just to take you through the evolution of concrete in terms of the water cement ratio. So we all know that we require a minimum water cement ratio of 0.26 for full hydration of cement. But in conventional concrete, we have a water cement ratio ranging from 0.4 to 0.6. This is provided generally for workability reasons. But in UHP FRC, we have reduced the water cement ratio down to 0.14 to 0.17 level. So this ensures that there is no excess water remaining in the concrete during its hydration process, and thus making the concrete much more impermeable and denser during the hydration process itself and casting phase. So therefore, we get a much denser concrete matrix, as you can see here. With 0.14 water cement ratio, we achieve this is the viscosity or the fluidity of the concrete that we achieve. So as you can see, it's a much flowable material, and so it's a highly flowable material which can be molded into any size and shape, and thus it's a much aesthetically pleasing structures can be formed. So just to take you through the stress strain curve for UHP FRC comparing with conventional concrete, is that basically you can see that we exhibit UHP FRC exhibits both elastic as well as plastic properties. You can see the much better strain hardening as well as strain hardening phases similar to that of steel. So what we would like to say here is that the UHP FRC is not just concrete, it's a composite material in between concrete and steel. So that's how it should be treated. Just to take you through one of the basically advantages of UHP FRC is that it performs excellently well in fatigue analysis also. So this is one of the dark areas of UHP FRC which are yet to be explored. But we have done extensive analysis and extensive testing on this UHP FRC beams. And therefore, in the bottom right-hand side corner, you can see that it provides much more better plasticity and can be seen a good cup and cone formation during the failure of UHP FRC. I'll just take you through a small video, basically just to take you through the construction process and the work that we have done in India so far. So we're executing almost 107 number of bridges across India, out of which 46 bridges are completed. So this is our plant in Pune, which is spread over across 15 acres of land. And we have also inaugurated a plant in Nagpur, basically. So this is the Nagpur plant. Right. So you can see that the casting is in progress. At the bottom, you can see the segments are being casted. So we have specialized or standardized our girders basically based on requirements, that is I, T, and U shaped girders. So these are basically standardized based on spans as well as the deck widths that we cater to for majorly highway structures, and we have also now ventured into the railway structures basically with the, and there are different so there are different girders for that. And we've received approvals from both RDSO as well as Ministry of Road Transport and Highways for implementation of UHP FRC across national highways and railway structures. So these are the post tensioning ducts, and this is the molding process that undergoes at the factory level. And as you can see, there is no conventional TMT reinforcement which is placed inside the webs of the concrete girder. So the girder is basically devoid or completely avoiding the reinforcement bars that are put in, and this is the mixing process. So these are the silica sand that you can see, water being added in the form of ice, and this is the steel fibers being added. So currently we utilize about 2% by volume of fibers for mixing of for producing this UHP FRC, which is of more than 155 MPa grade. We have a batch mixer, so that's an 8 cubic meter capacity batch mixer, so that 8 cubic meters is produced in one go. So therefore, all the girders that we produce below 30 meters length are segmental in nature. So since we don't provide any reinforcement, so they have to be converted into a form of segments. So you can see the flowability of the concrete during its casting phase. It's a highly flowable concrete with such small water cement ratio. And you can see the exclusive finish that we get over this surface. So it's almost like a glass finish because you can see the so you can see the light bouncing off its surface. Once it is casted, the concrete undergoes steam curing for 48 hours at 90 degrees temperature. This is specifically done to reduce its lifelong shrinkages and creep. So the shrinkage that you can see in UHP-FRC once it moves to the site is basically has zero shrinkage, and the creep coefficient that we cater to is about 0.2, which is almost 10 times less as compared to conventional concrete. So here you can see the compressive strength is more than 155 MPa for all the segments that we produce, and the webs you can see here are almost 100 mm in size for a 4-meter height segment. So this is so we've recently constructed a 102 meter long bridge. So these are some of the erection methodologies for these girders. And this is the post tensioning. Basically, all the other aspects of construction are similar to that of construction practices that we have in conventional concrete. The only thing that we've changed is basically the grade of the concrete for those bridge girders, and thus making those bridge girders much thinner and lighter in shape, and thus we can go for longer span. So as you can see, for this 70-meter span girder, the weight of the girder is only 150 tons. So conventionally, the same weight of the girder would have been somewhere between 250 to 260 tons. Reducing this dead weight, we can construct longer spans, and we can also construct bridges at high altitudes in a very difficult terrain with much ease, because the handling of such lightweight girders becomes much easier. So this is at various projects on Mumbai-Pune Expressway and in Mumbai. Yes. So this is the India's first 102 meter simply supported span bridge constructed with UHP-FRC technology. So this, as you can see, these girders are basically with 4-meter depth, and a temporary platform of 5 meters was erected, and the girders were casted and then put to use. So in the next slides to come, a much detailed presentation on that is included. And these are some of the other bridges basically. Right. So just now we are doing another world's longest UHP-FRC bridge in Nagpur. So so it is to be completed in this January. Once completed, it will be world's largest UHP-FRC structure. So some of the applications of UHPC technologies, basically you can find various applications across the sectors, basically bridges. Then you have civil and construction in residential structures, offshore and architectural features, and other defense applications. So case study, basically India's first 102 meter span structure. So you can see basically a 4-meter depth of girder with 26 number of segments for 102 meter span. Weight of each segment was about 20 tons. So therefore you have an entire girder weight of 450 tons. So in such a rural area, so taking a crane of about 100 or 1,000 ton crane was difficult. So we constructed a platform, and then on that platform we erected all the segments one by one, and then post-tensioned them and side shifted to its bearing location. This is how the erection was done, basically for each girder. And this is the photograph after the entire erection was done. And slab is completed. So as you can see here in this, there are 2 spans of 16-meter deck carriageway width in between each other, and they're in skew, basically over a canal at a 71 degree skew angle. And this is the current status of this bridge. So basically once it is completed, it will be put to use. Another interesting case studies is basically the Chandni Chowk interchange in Pune. This is a tabletop interchange that we have done with various orientation of girders at this location. So as you can see, this is a 60-meter long girder over the national highway with just a weight of 102 tons. So in normal concrete, that would have been weighing or somewhere between 180 or 190 tons. Yeah. So this is during the photographs during erection, and this is during the completion of these bridges. So as you can see, across the national highway, the girders are kept parallel to the traffic, but in approaches, the girders are kept perpendicular to the traffic here. So this is the one. As we were just seeing earlier, for the Indora-Digori flyover in Nagpur, So once completed, it is a 2.36 kilometer long elevated corridor with 34 spans of 60 meters and 2 spans of 90 meters each. So it is almost completed, 95% completion has been achieved. And this is the 90-meter span being completed just now. So it almost takes a month more to complete this bridge more there. So as you can see, for this 90-meter span, the cranes again were a difficulty. So we used a GSS system basically to launch this girder on the top and then place all the segments one by one. It is in the completion phase. Basically the crux of this technology is you can use any number of erection methods because these girders are lightweight to handle. So we have also utilized the precast slabs with stitch joints at the site to minimize site work. And as you can see, the segments are brought onto the site, placed between the two piers together. Then there are temporary post tension to align with each other, and then permanent post tensioning takes place. The another benefit of UHP of RC that we've taken is basically of zero shrinkage is that we don't provide any epoxy gluing to the joints. So entire joints are dry jointed since they're match casted, so they're perfectly matched with each other. And there is no requirement of epoxy gluing. So as you can see, this is the girder which is post tension. So during the night it is to be lifted by easy cranes, and these are some of the erected girders. Yeah, going ahead, basically to another application of UHPFRC is replacement of existing structures. So this is another interesting application for marine jetty structures in marine environment. Since we are having a much durable superstructure or much durable material in UHPFRC, so we can utilize that for marine structures in a much better environment. So this was a jetty which is constructed in Malaysia 12 years ago. So within the span of 12 years, all the normal concrete beams got spoiled, the reinforcement was exposed, and needed replacement very, very urgently. With UHPFRC, we constructed this jetty within a span of 6 months, and this was put to use. And now, basically, this was built in 2014. And now it is 20 times much more longer service life as per FIB codal provisions that you can see. So now with increased life and by use of the same substructure, it could be given. So this is the sustainability since everybody is talking about. So this is a CEPP model basically which is given by FIB 2020. It has been introduced basically just to calculate the effect of concrete on the conventional concrete. So just to give you an idea, basically the CEPP model is provided to the designer to evaluate the concrete potential of a sustainable structure basically, or the effect of concrete on environment. So this is a CEPP value. As you can see, the concrete grade basically, as the higher the grade, the more is the CEPP value, and the more because the tensile strength that we get currently is about 12 MPa.
So will that not, I mean, a normal concrete also, at lower cost, that will also serve the purpose. Have you, because you're comparing without post-tensioning concretes, you have given the comparison.
Right.
But in the video, we are seeing that there are structures where you're doing post-tensioning.
Right.
And this being a tension member, why you're post-tensioning it?
So basically, we're not trying to utilize the tensile strength of concrete in this entire thing. We're trying to utilize the compressive strength of concrete in UHP FRC girders. The tensile strength is utilized in the transverse direction, basically. So if you have the webs in the transverse bending, it is completely utilizing the tensile strength of UHPC. But in what happens is we're reducing the section. So thus we are imparting much more compressive stresses during the post-tensioning part, and thus we are going for longer spans. So that is how the methodology is working in that.
Okay, thank you. I think there is a point in it. You could compare. I did not understood his question. I got it. Right. Anyway, so we move on. Thank you very much. Give him a good round of applause. And it is increasing in India, and I think there will be ways to handle and understand better in time to come. The next presentation is by Engineer Pierre Hoffman, if I pronunciate it correctly. Right, and sustainable and innovative designs of concrete lining from mine tunnels to mechanized tunnels. So very apparent, and these days India is going in a big way in tunnel construction, and we would love to hear you on that. Floor is yours.
Thank you. Yeah, tough mission to talk about this topic, and especially as you say in India in a short amount of time. I'll try to focus on projects that have been recently executed or upcoming in India. And so we'll be talking again about reinforcement and I would say innovative approach. I think it was very interesting to hear that in continuation of the previous presentation, because you'll see the synergy between the different way of reinforcing concrete. In just one slide, so I'm working for the company Dextra. For those who might not know us, we've been in India for more than 20 years now, and you see founded over 40 years ago. Our main job is to manufacture and supply solution for the construction industry, and in particular our number one business is concrete reinforcement products, so around couplers for steel rebar. Myself, I'm in charge of the geotechnical product line, ground engineering, so which is the reason why we'll dive into tunnels. So I'll bring you underground if that's okay. And again, we'll be focusing more on composite material today. So again, we also had some earlier presentation during this conference on composite material, so I'll be brief, just to be sure we are clear about a few characteristics about the material. So what I mean by composite material, so talking about FRP, so fiber reinforced polymer. Those are products made primarily of fiber, so either glass or carbon. There are other type of fiber also available, but at Dextra we focus on those two fiber. So the product is made 80% of fiber, and again today we'll focus on glass fiber, and inside a resin matrix. So the resin matrix can be polyester, vinyl ester, or epoxy, and the choice of which matrix to use, it depends on the application. So actually for many years, those products have been used in tunneling industry for temporary application. Big common way is when you have a underground tunnel construction, the TBM, the tunnel boring machine, has to bore through concrete. We've done this in many cities around the world. We have Bala here from Chennai, and we're busy with a lot of soft ties in the Chennai Metro. Phase 3, is it? Phase 2, thank you. So very common to have this application, but what I'll be focusing is more on permanent application. And again, something important to highlight is we have to use different resin matrix when we do permanent application, so vinyl ester or epoxy. So how are the composite material produced? We have a continuous manufacturing process, which is called pultrusion. And so all the fibers are traveling in the line, in the production line at the same speed. They are binded with the resin matrix, and it's a thermal reaction. So you see the curing tunnel or the mold will transform the resin from its liquid state to its solid state, and it will stay like this forever. So typically, if we look at about the rebars, we have to introduce during this manufacturing process steps to bend also bars if you need stirrups. You are mentioning stirrups. If we need stirrups in GFRP, they have to be formed during the manufacturing process because GFRP can't be shaped or reshaped, bent at a later stage. Last few features before we dive into the application. This is example of the geometry of a GFRP bar. Actually, if you're interested, we can show you samples on our booth at the exhibition area. And something important to highlight why the bonding is so much greater than on a steel rebar is we are relying on two different mechanisms for interlocking with concrete. The surface has a sand coating on the surface, which creates a lot of roughness. And on top of that, we have helical wrap that creates surface deformation. So you can see that steel is generally quite smooth, so it's really the ribs only that will provide bonding. Here, we really have the combination of the two mechanisms, and thanks to that, we can guarantee 9.8 MPa in bond with concrete, which is much higher than what you would get from a steel rebar, probably only 3 or 4 MPa. Okay, so that's also one of the features that allows to optimize design using GFRP, typically development lengths or lap lengths. For example, in the latest ACI, we can reduce lap lengths to 24 times the diameter, while it would be common to use double of that with steel rebar, 40 to 45 times the diameter. So just to conclude again on the material specificities, this is just a summary of the advantages. So the material is much stronger than steel, but we'll look at tensile property just after. It's also 4 times lighter, so it makes it a very easy material to transport and install. It's durable, it's completely resistant to corrosion. We'll see maybe just a few aspects of life prediction, but it can advantageously replace steel in many cases. Yet you will see that probably some of the best interaction possible are not necessarily using this material exclusively, but rather find hybrid design where we can advantageously use steel or steel fiber and GFRP in the applications. So why I say it can replace, but maybe not in all cases, is because the mechanical properties are fundamentally different. If you look on this graph here, a typical stress-strain relationship, actually we can see that in red would be your typical steel rebar reaction, so the response. So we find the yield point. This point I'm not sure you're going to see here. We can see the yield point, and then as we know, a lot of ductility. So that's a very different behavior from GFRP, which is here in blue, the straight line. So we can see that the modulus of elasticity is very different. The initial response, the curve, it's a straight line, but the angle is different. So we have modulus of elasticity that is between 45 and 60 GPa, so around 4 times less than steel. However, it's a straight line. So it's what we call linear elastic material. No ductility, no yield point. Is it better? Is it worse? Again, much higher tensile strength. The conclusion is just it's fundamentally different from steel rebar. It's completely different. And for those reasons, it's absolutely necessary to use different design codes when using those materials. The same was presented in conference yesterday. So if you look outside of India, in the last 3 years only, both Europe and America released standards that are for design and for material specification using this material. Even though material exists for more than 30 or 40 years, you have bridges in North America that have been reinforced with GFRP over 30 years ago. The codes are relatively new, even outside of India. And in India itself, at the end of 2023, 2 IS standards have been released. So 18255 and 18256, respectively, for testing and specification. So the good news is now in India as well, we have standards to apply GFRP rebar in concrete. So that's fundamental for the adoption of the material. And again, here you'll get the provision to understand the differences with steel. One thing, however, to note is India doesn't have yet a design code. It's in the making, so I mean, in the meantime, we have to rely on international code, which generally the ACI is being used. So, with all this information, then what does it mean for tunnel project in India? Again, we have fundamentally changed the way GFRP is used in tunnels, because instead of placing GFRP in the face of the tunnel, which would be the temporary application where you break. So again, if it's in a TBM tunnel, mechanized tunnel, you used to place GFRP in the face for the tunnel machine to go through. And if you look at mine tunnel or mining, even mining, people would place GFRP just in the face so that it's stabilized and easy to break. We recently changed that, placing GFRP as a radial support. So again, that's why we're looking now at the lining of the tunnel and how GFRP is having interaction with the lining. So this is now meant to stay in the final structure of the tunnel. So again, it's applicable to mine tunnel, it's applicable to a mechanized tunnel. We look at that. However, to do so, we have to look at several parameters that prove that the material can last. I just decided to focus on one parameter, but there are more. And again, for time constraint, I just presented this. This is an accelerated aging test that is formalized as per ACI and ASTM standard. And so we place GFRP bars in a water solution with a very high pH. You see close to between 12.6 and 13. And so at high temperature, 60 degrees, so we replicate the condition of moist concrete over a long period of time. The high temperature gives this accelerated aging. And we can see that the retention is 85%, which is what the code imposed for us to apply as a reduction factor. So we can rely on 85% resistance of the rebar over time. There are other aspects like creep that would be also qualified, but again, I decided not to present them. If you have questions, I'd be happy to answer. Consequence of that, it's possible to design, again, tunnel with permanent GFRP rock bolt. What I'm showing you is the largest oil storage cavern in the world, which is in the UAE. We supplied 600,000 GFRP rock bolt to this tunnel. You have enough to store 45 million barrels of oil in this cavern. And India itself has a big network of strategic and commercial oil reserves. So companies like ISPL, HPCL, they manage those resources in India, and the same technology is applicable. So we are hopeful that the same will be used very soon in India. The reason I mention this is even recently we formed, and I've been asked to lead the initiative in the International Tunneling Association to create a working group on GFRP permanent rock bolt. So this is also happening at international level, and we have actually a kickoff meeting next week only. So this is really a new initiative. Has it been done in India? Absolutely. Just reporting now on a tunnel that recently had breakthrough. The highway is not operational yet, but the tunnel activity is completed. So you see this is a large size tunnel, 22-meter span. Part of the Delhi-Mumbai Expressway. This section is the Delhi-Vadodara Package 15, which is located in Kota, Rajasthan. Over 100,000 rock bolts are used on this project, with Dilip Bilgan as a contractor, Infinite Civil as a consultant. And so this is NHAI projects, National Highway of India. And Bedi Consulting has been helping us. I'll just show you a few pictures to let you understand a bit the geology and the complexity of excavation. I don't know if you have many tunneling experts here, but this is what we call a multi-drift sequence, where excavation has to be done, again, sequentially to ensure we don't have a full face and limit convergence. But you can see a bit the type of underground work, and again, do you appreciate the size of the excavation? Well, I'd like to explain a bit the value engineering we brought to this project. Option A was the original design with steel rock bolts. And I don't know if you know, but when you install steel rock bolt during construction of a tunnel, they're just meant to last a few weeks, or let's say a year, and that's it. Why? Because the permanent lining that is casted afterwards will take all the load. So we know they're going to corrode, and we don't care. It's fine. They are not having any permanent structure. So what we decided is to offer a design where we would use GFRP rock bolt instead, permanent grade of GFRP rock bolt, so we could reduce the concrete lining from 300 to 150 millimeter thickness. So what's the idea here is, instead of relying exclusively on concrete, we have a combined effort of the concrete and the rock bolt, which in any case are needed. They are in any case, rock bolt are installed, they are necessary at temporary stage. But because they're permanent, we could reduce by half the thickness. So what does that mean? You reduce the excavation by 5%, because now you cast less concrete. You can even excavate less during your tunneling activity. That actually reduced by 5%. Those 150 millimeter, you reduce 5% of rock you don't have to muck out. We reduce, you see, almost by half the quantity of concrete. And we reduce dramatically steel, because instead of using steel rebar, we were using steel fiber for the concrete. So fiber reinforced concrete, secondary lining, and all the steel rock bolts are replaced by GFRP rock bolts. On top of that, I didn't show here, actually, the productivity was improved by 20% on average, because obviously it was much faster, no steel fixing, and also, again, pouring 150 instead of 300 millimeter. Just to explain, the same kind of optimization can be done on mechanized tunnel. So this is an example for TBM tunnels, so with precast segments. And here, the idea is to use a combination of GFRP rebar and steel fiber, but actually pay attention to the picture here. You can see that there are very few GFRP rebar, and they are strategically located on the perimeter, on the outside of the segment. The reason is the peak load in precast segments, once they're installed, is actually the thrust force of the TBM that applies on the faces of the segment. If you don't put any reinforcement, you have to place a very high dosage of steel fiber to cater for this temporary stage, which is just the thrust force of the TBM. So placing GFRP rebar on this location, you can reduce significantly the dosage, which brings a lot of advantages in the precast yard. And also those GFRP rebar will help a lot with early strengths and stacking capability of the segment. So I just listed here a few advantages. I won't be able to go through all of them, but I just give you some ideas of the optimization of having this such hybrid design. And so this was a calculation made by Tanebori Valley project, which is ongoing, and eventually we're not able to accommodate this design due to, I would say, a long time. But anyway, I'll just explain the logic of it. We made the calculation on such a large diameter TBM, and there are many upcoming one in Maharashtra in very difficult geology, hard rock, basalt rock. And so through the reduction of the thickness of the segment and change the dosage, we were able to offer an alternative design. So again, with GFRP rebar on the perimeter and combination with steel fiber. And that proved to be a very cost-effective solution. This is the solution you see here in purple, which can be 20% cheaper than using other type of reinforcement. So just to conclude, I'd like to give you a bit of sustainability consideration over that. How does GFRP rebar compare to steel rebar? I have a comparison with steel rebar, and the average in the world is 1,400 kilo per ton. This morning, a gentleman was mentioning in India it's even 2,500 for steel rebar, the emission of CO2. So you can appreciate that GFRP, because it's so much lighter and stronger, would actually reduce by closer to 5 times compared to traditional steel rebar. I understand you have also green rebar in India. How does it translate on a project like the TBM segment? Without reducing the concrete thickness, we could already reduce by 64 the reinforcements, and that could lead almost, you see, more than 8% reduction. While on the GFRP rock ball case, because we were able to reduce also by half the quantity of concrete, here the saving is dramatic, which again shows that GFRP enabling reduction of the thickness of concrete really makes a difference. And just to conclude on that, I just wanted to highlight one last thing is GFRP can even help changing concrete in other way, because we are also now offering sea sand and seawater concrete, which is helping the circularity or using different type of material. So very soon ACI Committee 243 will release a guide on seawater concrete, and that's the next step. Maybe I'll come another time to talk about how we can use GFRP in a sea environment.
Okay. Thank you. Thank you very much. Wonderful presentation. I think a new insight. There are lots of projects started in India also, but long way to go. Yes, please, go ahead.
I see a basic flaw, or in this GFRP. If you go to the slide where we have shown the modulus of elasticity, so there is an advantage in steel because it has got a very high strain before it breaks. This one, if you see, the strain is very high, and that is the reason why while designing, the structural engineers take into account 0.2% strain, because if at all the design has been a fault, there is enough, enough time for people to move away. But here, if you see, the strain, the failure strain is very less. If I had to give 0.2%, it would have been less than the steel.
Yep.
And the failure is sudden. It is not like, where there is softening point. So this is, I don't know how ACI, the code has handled that problem, but I see this to be major challenge in designing the structure.
You're absolutely correct, and it's a very common objection or question.
Yeah, you can answer.
So to explain, I would say the essence of my presentation today was you will still have a lot of steel rebar used in your construction. And the whole point is to understand the advantages and disadvantages of both material. And they are applications were mostly dictated by the tensile properties. So where GFRP is mostly used today is all slab-on-grade application. Not only, I would say, temperature and shrinkage. We also do very heavily reinforced slab, where it's fully supported, and therefore you are less governed by deformation. So, of course, if you think about high-rise building and changing everything to GFRP, the ductility and in case of seismicity can be a big question. But actually, a lot of work is done today on hybrid design, even for a seismic environment. Maybe the best solution is not to have both the straight bar and the stirrup made of steel. Maybe having some of them made of GFRP and some of them made of steel working together would work much better. So I think as engineers, we don't say stop using steel and start using GFRP. Far from that. Actually, GFRP, at Dextra, we sell more steel than GFRP. This is the bread and butter of our company. Actually, we say as engineers, it's important to understand, and I will be the first one to say yes, advantage, disadvantage, strengths, weaknesses, so that as engineers we understand and then we design. If you want after that, I can tell you how ACI tackled that. But really, I think the essence is, thanks for pointing it out. It's true. I'm not hiding or anything. It's quite the opposite. Our best design today are hybrid design, where we use the combination of the two materials to maximize value engineering.
Yeah. Anyone else? I can take one more interesting. Yeah, please.
Quick one. In tunnels, you told me the bolts, na? So how the type of rock decides the length of the, suppose the poor rock is there, you can't put bolt, na?
So of course, the concept of doing this kind of reduction of permalining, we need to be in competent rock. Okay. Otherwise, you have to go with a massive secondary lining. But it's still many cases where we can design like that. So again, as engineers and internaling, it's a very common activity. You do, of course, Himalayas would be. But you say that, but in the Himalayas, we have an upcoming project now in Rishikesh area. But again, one package is suitable for that. I think there are maybe 10 or 15 packages on this project, and the other might not be applicable. So similar to the question of GFRP is not going to replace every steel rebar, the same thing, even more in geotechnical application. We always do a lot of sampling, understanding. You know, as the project continues, you're continuously monitoring and confirm whether this is suitable or not. So the same would apply.
Right. Thank you very much. Thank you. A big round of applause and nice presentation. And I'm sure that there'll be more questions to discuss. And just a note that this is something, a material when it is evolving. So day one, it doesn't replace anything. I think he has answered. And there are different ways of handling it. And maybe just because the code is also evolving, right? So if something is not good, you try dealing with either in situations where it is not required, or there will be some tailor-making for the material, right? There are other issues also. I think the fire is one, and there are some other issues. It is not that it is without problem, but yes, we have to look at the advantage and try engineering it for the good. Moving on to the next presentation, I invite Engineer Amit Barde, who will be speaking on modern trends in building construction with new mantra of mechanized and digitization. Oh, very good. So in civil engineering conference, some digitization, and does it involve anything on the AI also for analytics?
It does. We are using
okay.
some. But
good, good. Carry on, please. I don't want to start from there. Thank you.
How are we doing on time? About how much?
You have 18 minutes to speak, and I'll stop you at 18 minutes, maybe then a couple of minutes more.
All right. I think good evening everyone. One of the last sessions, so what we said, I think when Dr. Subbu called, I said we will do a compilation of various technologies he wanted to summarize. So what you will see is going to be a rush. I will touch base, but the idea was to, from the industry perspective, whatever that we have been doing in last, let's say 5 to 6 years in various aspects of building construction, right? So this is focus. I come from buildings and factories. Focus area is anything that relates to buildings, right? So we do a spectrum of work. Buildings like, of course, Narendra Modi Stadium, structures like these. What you see in the picture is high-speed railway. The girder is 40 meter long. It's about 1,000 tons. One single cast pour. The project team is more excited about the straddle carrier that we have built in-house. Right? That's the mechanization what we are talking about today. Atul Setu, we just recently delivered long span structures, concrete and steel combination. What you see in this picture here is 150 meter long, OSD, the orthotropic steel deck, 12 meter wide, installed in about 2.5 hours. Right? What used to take months to do these kind of spans, we are doing in hours. Again, that site team is more excited about that barge that we have built. Right? And if you want to take a scale of that barge, you look at that square. It's not quite obvious in the first view, but these are the people standing, and then now you look at the barge again. Right? It's a football field, long barge, hydraulically controlled. The motions in heavy winds itself, but the maximum up and down it will do is about 3 to 4 millimeters. And that kind of technology, that kind of sensitivity we are looking at. Projects like coastal roads, undersea tunnel, metros, you name it, and we are doing it now at much faster speed and scale, right? So this is where I think if you want to take one slide home where India is today, and that's the topic, is the mechanization and digitalization, right? And the business excellence, what we look at, if you want to look at as a construction or as a manufacturing industry, it revolves around that. The missing pieces, however, what gets usually overlooked is that mechanization is bringing efficiency. That efficiency is being tracked by digitalization to see what innovation is needed to do more mechanization. And a lot of times is that these are taken as buzzwords, saying, everybody's talking mechanization, everybody's talking digitalization. But we are doing that in a real sense now, and that's the flavor I'm going to give you. Now, when I say this, it seems like a big change for the industry, but construction is, the inertia is pretty significant, right? We have been doing the same things for long. Last decade has been different. Again, what we have felt is that marginal improvement is what will push you to that next level, right? And this is what you will see everywhere that we do in buildings itself. And if I have to again summarize everything in buildings now, what we have looked at is, if you start from the bottom of the curve, a low-rise building to a high-rise building, how the industry evolved last decade, right? It's drawn on a S curve with a reason, saying if you take a derivative of that curve, the derivative is going to show you the speed of change in the technology. In low-rise, it's fairly moderate. In the mid-rise, it's picking up significantly. You go high-rise, 50-meter tall building, it's not as much. Whatever we do, ACS climbing systems are fine. Low-rise, whatever we do for ground plus 4, we are dabbling with 3D, but the change is not as much. But the mid-rise, which is your 10 to 30 story, 40 story, is where you will see start of changes. But if someone says, okay, in all that, what are the two things? Then it's the hybrid system of the new age. No one system will come and win your hearts or your performance. But on the right hand side, if you see something that is off-site, may it be precast, may it be steel, may it be pre-finished. Going forward in India, the kind of manpower challenges we are having, kind of skilled workforce challenges we are having, we are going to move towards a philosophy where as much as less possible at site. And that's what you will see in all these systems, is how to improve productivity and reduce your manpower. We started with 3D. We have been doing that very niche technology. It was a wonderful hobby for 3 years for all of us to develop this, bring it to that. Whether the industry takes it up or not is up for the grabs. But we have done multiple buildings. Everybody, I think, is talked about 3D. I'm not going to show the videos for long, but this was one of the first building that we did for the post office. It was handed over to the client in about 44 days. But what we are looking here is not the speed. In the video, you should look at that there were only 5-6 people working. If it's conventional, you will have an army of people working, right? So we took that same thing to a larger scale, and we have finished now about 50,000 square foot of construction using the 3D system. This is a truly example of mechanization where we had at one time 3 printers working simultaneously at that project with about 10 to 15% of people than what would need in conventional. The client was extremely generous. They said, whatever technology I want to take the best of it, so no external plastering. They said, we will paint it as is, we will live with the striations. But if you see, the best of the technology came in that one building. We detailed it out where it's circular. The 2 floors are offset. There are circular beams. If you would do this in conventional ways, you would spend months building the structure, building the formwork. But with the 3D printer, one printer, no movement, that building was done in about 20-22 days. We took it to the villas. I won't run through the videos, but we took it villa where the client said, I want to build this villa in 3D. I will finish it my ways down the line. So this is for Prestige in Bangalore. We said we'll do that with all the niches and everything. Right hand side is the 3D printed where the arches and lintels and everything horizontal we did precast. Slabs were still cast in place. But 8 villas were done and they're standing with 3D concrete printing. So it's up to you what you want and how you want to utilize. This is another small building where everything is different in all planes. It curves, it pans, it's in and out. Exactly per the architect's vision, the buildings you are able to deliver, because that mechanization doesn't care what shape and how you are building as long as some parameters are met. Right? So that's 3D. Another we are dabbling is the hybrid structures for steel and precast depending on what speed you want. But this building was done in DRDO, Bangalore. Whatever you see in the picture except the foundation was done in 45 days, handed over to the client with the furniture in. Extremely large planning, 6 months of planning, but everything was kept. Steel structure, precast slabs, multiple cranes, day-night working. But to the plan, if you plan it well, if you do the logistics well, if someone wants to build the buildings, it doesn't even come at a premium anymore, right? With the whatever times you are saving, we are still doing and operating at the same cost that you probably would be on the conventional. But more than the speed, what we are now looking at is the assured delivery. Right? I tell you that I'm going to give this project in 12 months and I deliver you in 12 months instead of 16, 17 months because of the challenges at site. Precast construction, we have been doing that. I think one of my main portfolios is precast construction. So we are doing these large houses at a very large scale without going into too many details, but the proof of the pudding is about 6,500 houses built in about 2 years, which would take anywhere between 4 to 5 years. Lot of finished buildings. The technology has evolved in last decade where we are able to use it on a large scale. And then we wanted to show it the best of the best technology is a 12-story building, what usually takes about 3.5 months. We built that in just 36 days. A 3-day floor cycle. You put more resources, you put your planning, and the building is built like a Lego blocks. The first floor was 3 days. Balance all floors were 3 days, exactly as planned. So like I said, more than the mechanization, the assured delivery is I plan and I deliver to what you want. And that is shown. We finished that building also in further 80 days, so total 96 days the building was handed over to client. Another in precast is a commercial building. So we are looking at this parking structure, about 1.5 lakh square foot of built up area, columns, beams, hollow core, 41 days, 6 stories, 360 car parks is handed over to client in 41 days. And I mentioned about that prefab and off-site construction. At the last leg of the project, we said, why even paint it at site? So we painted those elements at the factory and shipped it and installed it. And this is where I think the industry will move further. We are now doing large projects here. So this is our one of the latest precast factories, about 3.3 lakh square foot of built-up area, right, per year, one of the largest factories. But what we are proud of is the mechanization. That's the topic. I think this is one of the first hydraulic, fully automatic battery mold. You get both side finish in the factory. No paint, no putty, no grinding, mold finish. The green system is your concrete delivery. So the shuttle goes under the batching plant, collects the concrete, puts it into your panels in 6 minutes. Most of your quality issues is because the TM is waiting, nobody knows how much water goes in. This is no manual intervention, directly from the batching plant to your panel, put in at 60% reduction in the workforce, and you are getting much better panels that will directly go. Other things we are doing, we are going longer, we are scaling it up. So if you see, our philosophy 10 years ago was 1 room, 1 panel. We moved it to 1 panel, 2 rooms. Here we have done a 10-meter long panel which covers 4 rooms. That many less elements, that many less joints, that many less issues to worry about, and the speed becomes higher. What next we'll do for technology is, why do 10 rooms? We do the whole room itself. So we are looking at that volumetric now. We are taking some of the cues from the outside world. We started with mini volumetric. So what you see is right hand side pictures is the entire finished toilet that is inside that box, and that is being placed in the building, and the building is being built around it. Why? Because your toilet and bath units are the most complicated units to finish at different heights. So you put everything finishing in the factory, you control it better, you have much superior quality control. Believe it or not, I am looking at removing the waterproofing, because the factory produced concrete M50 grade. We put the water for 3 days and it doesn't seep. So we can do that same thing we did in commercial, that Bangalore DRDO building I showed you, we changed the toilet blocks, which is much bigger, but again, whatever you see right hand side is finished in the block and kept. That we are extending it to a much larger scale now, where one of the demo projects for IIT Madras, the entire room is being finished and then kept. So the right side building is what total precast frame, and the units are, the rooms will be finished and kept in the building. The unique thing is those rooms are light gauge steel and dry walls. And the very new concept in sustainability is repurpose. So what IIT Madras said is the entire floor you give me column beam frame, I put the hostel rooms. 2 years down the line I decide that I don't want the rooms anymore, I want a large hall. We can dismantle those rooms and take it out, and they can use that to whatever they want. On a similar fashion, we are doing one in Ayodhya now, a hotel building, fully finished rooms. You keep it, install it, and put it to the site. Remember that off-site construction. We are trying to reduce the activities at site, do it at factory level. Same in commercial buildings. This is Jamnagar solar project, 250 liter long building, electrical, total precast. Seismic detailing is very different, so we said the beam column joints are precast but monolithically cast, and then we install the building. Right? Sustainability, we call these SSEB systems, self-sustainable energy efficient buildings. This one building is operating at 25 degrees Celsius in Ladakh with absolutely zero electricity or energy, solar, wind and geothermal. Last 6 months is operating without any electricity and at that 25 temperature. Facade is evolving. We are looking at energy facades now, so that is one of the technologies. This is our one of the corporate buildings we do lighting and everything. In MEP, we are moving towards off-site or modularization, where the entire room or floor MEP is built together, boxed it, ready, ship it to site, either before the slab or after the slab. Biggest benefit is one agency, one anchoring. There are multiple agencies doing multiple anchoring. Somebody is messing with each other. This doesn't happen here. Everything is assembled together and then fit it with limited anchors to your site, and then you move out quickly. Same concept, we said we will apply to vertical shafts also. So even the vertical shafts we have done modular, where entire piping is done. Right. Where we are moving now is mechanization of the next level. So we are now looking at robots that will tie the cages. This is in production now. Another month, our factory will have the two robots which will tie the cage. We are looking at robots that will put the block by block. We are removing the block by block construction itself, but whatever is there, you put with the robots because of that workforce challenges. Switching the gears slightly is geopolymer concrete. Again, that is one of the areas, but you see thousands of non-structural elements. The geopolymer, the zero cement concrete, we use it our factory also for nominal elements. We have done now one footing also of a temporary factory, because my factory temporary, I can take that call, where one footing is going to sit there for 3 years, which is zero cement concrete. We are monitoring it closely. Textile reinforce is coming in also. Very inception stages, but very thin elements. These are all 50 millimeter thick. Textile reinforcement, no steel. I don't have to use minimum cover. Same thing for metro piers. We have done that as a pilot. Recycled aggregates is something of our interest for sustainability. So wherever our temporary factories, we have now almost more than 20,000 square meter of recycled aggregates installed floors that we are monitoring. Because these are my temporary factories, we can take that call, but absolutely no performance challenges. And this is my heavy precast factory floor. There we are using this. Right, so that's the various technologies in the mechanization space. How we do digitalization, right? That's the last part of the presentation. 1.25 lakh elements in that project in precast. Right? When it comes to that, I cannot rely on my Excel spreadsheet anymore, saying how many are done today, what kind of planning is done, what kind of reports are generated. You have to rely on the BIM models. It's not a luxury anymore. Digitalization is not a luxury anymore for us. We have 11,000 pieces of equipment now connected in IoT. Each and every data is coming in at various levels, with the central model concept, where the old model of reports to various parties, from party to party, we are trying to remove. BIM was there already, but that BIM is now having the dialogue with all parties simultaneously. So whenever he click the report, then this panel is installed. instantaneously on portal, all these parties know that these panels were installed. We are taking that to the next step of temporary structures. So all our formwork drawings now, all our safety drawings are automatically generated using that AI concept without having multiple trades generating those drawings. So I have one BIM model, the AI runs and it will generate my formwork drawings, it will generate my safety drawings. Tender evaluations. This is Varanasi Cricket Stadium. We will be handing it over in March next year. This video was done before tender. Right? We have a thumb rule that first thing a project manager should visit site. Unless you see the site firsthand, you don't get the feel of the project. Those days are gone anymore. These videos are prepared in 3-4 days, but that gives the project manager plus the site plus the client in exactly how I'm going to operate the site. It was done only to show the site logistics, where I will do my precast yard, where will be the workforce colony, how I'm going to build the job, how people are going to walk in and out of the site, how my trucks are going to walk in out of the site. We are using the point clouds now. This is Delhi Stadium, Delhi Station, point cloud, millions of points. But what used to take at least a week or 10 days, this is done, the scanning is done in 3 to 4 hours. And once it's done, you ask me how many light poles or how many trees or how many buildings. At a click of the button, we are able to generate that information using the point clouds. BIM, another level we have taken where all my precast elements, whatever those buildings you see, even a 6 millimeter link is modeled. Its quantity is taken, its alignments are done, all the dowels, everything is through the BIM models. Once I have those BIM, I can track that planning, what I was mentioning, that each element out of that 1.25 lakh elements, when it was cast using what mix, who signed off the checklist, where it was installed, how long it sits in the yard, which truck took it to the site. Real time we are able to track the tower progresses, we are able to track BIM models, daily progresses are going. We use the maturity meter now, where real time I am tracking the strength of the concrete itself, so I can quickly demold the elements and efficiently take it out. Laser scanning is picking up significantly. Earlier we used to see these videos on YouTube, but now fascinatingly this is the video on our site, and we are using this on the day-to-day models where how the temporary structures will do, where my piping, where my routing will go, using the twins. And this is day-to-day is being installed. Last 2-3 slides and we are going to do. The AI, the question you asked is, these are the 2-3 things that AI is evolving, but diesel bowsers. We used to have trouble saying, I don't know how much is diesel being used, how much is wasted, who is controlling, who's tracking. So this is now all digitally controlled. Now they talk to each other, and unless they have a portion quota, the pump won't dispense the fuel in that truck. So the truck has a RFID, it will talk to saying, this month I have to use this much maximum, I use this much. The person is only putting the nozzle in, the dispensing is automatic, we are tracking it, we are able to control that wastage a lot better. All our batching plants are connected, efficiencies, material, all that database we are building over 10 years where that AI is going to come in picture now. And we are already doing that is the predictive analytics in terms of AI. We are able to predict if a site will have a safety incident based on the initial days incidents that are being logged compared to the 10 years of data. And so the safety guys are getting saying some observations are repeated, this is something off with the site, I should look at it, they go visit, check and take it up. Workman training, workforce training is happening on the VRs now. They enjoy it, they understand it, language barriers are gone. The trainings, the retention is much, much better. So where we will go and where we will end in terms of the sustainability theme also that this conference has. In our mind, where India stands, where the scale of projects is, right? Somebody we were discussing that China is doing 2,000 million ton of cement, India is doing 450 million ton of cement, and US is doing only 100. At that scale, with these technologies, if we do the low-hanging fruit of wastage reduction, there is countless, we don't know sometimes how much is getting wasted. If we can reduce that using this mechanization, using this digitalization, not only in terms of materials, in terms of your design, drawing, planning, material processes, I think that would be one of the biggest contributions from India. So with that, thank you very much for your patient hearing.
Thank you, Mr. Amit. And I think I'll skip questioning because you have taken already more time. And now we move on to the last speaker, and you can have some discussion later on. It was some of the things, number of companies have started doing that, and I hope that future to reach us to digital twin in construction also. Yes. Okay, so after finishing this session, we have to go for the award function, which is in the main hall, and then we'll move to dinner after that award function. So Mr. Ajit Chaube, is he here? RDC India, ultrafine materials for sustainable high performance concrete, enhancing performance parameter and real world case studies in Indian projects. So welcome, and I again request you to keep time on track, right? Okay, thank you.
I'll try to be as fast as possible.
Thank you. You have 18 minutes, and so that 1 or 2 questions we can take up.
Right.
Okay, thank you.
So, just to make your work easier, sir, I would like to go right at the end. I'll try to do the different way. I'll start with the conclusion. So, so that way, I think.
You are the best person to decide where to start.
Right. So here in this study, sir, we have concluded that the cement can be reduced with ultrafine, and to a huge extent, and even for normal grades, because ultrafine GGBS or microsilica, these kind of materials, they have been used only for higher grades. But here, this is a case where we have been, for one of our customer, we have been able to reduce the cement content, also the cost. That part I may not be able to show because it's a very long study. And it also can significantly contribute to the construction sector to bring down carbon dioxide emission. Now, this was one of the most important findings here, that increase in strength of concrete was directly proportional to the square of ultrafine that we had added into it, up to 5%. And we had limited this study till 5% because beyond 5, when we move, the admixtures that are commercially available today are not able to handle this microfine materials and dispersing them. So coming back, how did we come to this conclusion? So this is the equation that we developed based on study. So what we did was, many a times the research when we do, we say that this much cement, this much ultrafine will give me this much strength, this much cement gives me the strength, but we never are able to get exactly the same strength. So what is the answer? The answer would be to model, a concrete strength based on the water cement ratio and ultrafine percentage. And this is the equation that we got for the strength. The strength is equal to minus 57.07 plus these numbers e raised to minus water cement ratio. And if you see multiplied by 0 square, that is the percentage of ultrafine. So with 0% of ultrafine, the water cement ratio, if you calculate this, the value of water cement ratio for whatever materials that we had, the water cement ratio required to get 35 MPa strength was 0.377, which translates to 0 kgs of ultrafine, so 298 kgs of cement, and fly ash percentage being the same, 25%. So you would get a strength at 298 and 100 kg. Whereas if I use 5% ultrafine, so you see there is 237 kgs of cement that is required to get the required strength, 35 MPa, fly ash of 80 kgs, 25%, and an ultrafine of 17 kg. Thereby, there is a significant reduction of 61 kgs of cement. Now, how did we come across this number, this equation? This is where, the entire studies. So this is the equation that we got, the predicted strength versus the achieved strength. So if you see the equation, it has got a very good R square value, all for 3 days, 7 days, 28 days. And this is not just the equation. In the strength, whatever we got, you will also be able to see 2 mixes where there is no ultrafine and one in which there is ultrafine, you are getting almost similar strength, but the 60 kg or that much amount of cement reduction is visible, is inevitable. So coming, how did we design this trials? So this was basically for one of our projects in Mumbai, where we wanted to help them to get GRIHA certification to reduce the amount of carbon dioxide, the embedded carbon dioxide, and also to reduce the cost. So this was a 4-dimensional problem, and we did solve that. And this was the plan of trials. So if you see, certain similar kind of studies used to be done earlier, almost 50, 60 years earlier, with Malcolm Johnston from UK, who tried to do water cement ratio on x-axis, y-axis was percentage of fly ash, and 150 trials he had to do. But here with this statistical, we got the study in just few number of trials, some around 18 number of trials. And if you see these same dots that you see with water cement ratio and percentage ultrafine, these dots are nothing but these trials that you see. So these are the trials that we did, all this. And these are the strengths that we got. So connecting those points in an imaginary, 3-dimensional plane, we got the equation. So if you see here, the 14th trial, 36.66 MPa strength, and the 7th trial, 35.1. So there are many such pairs of trials where despite cement being less and ultrafine being used, you are getting the same strength. So if you see the 7th trial is with 12.63 kgs of ultrafine and 246 kgs of cement, and 14th is 296 kgs of cement. So there is a 50 kgs lesser cement and you are getting the same strength. So there are many such examples in this, where you'll see as the percentage ultrafine keeps on increasing, the strength keeps on increasing, and you are able to get the strength with much lesser amount of cement. So this is the study with 0.38 water cement ratio. This is the percentage ultrafine slag. So the strength keeps on increasing. This is with 0.44 water cement ratio. So in this plane, there were only 2 trials. This is the error estimation. So what we did was same water cement ratio, same percentage flash. We repeated the trials and we tried to find out what is the error in our trials. So basis that we could judge how much confident we are about the strengths. In this plane, we got almost the same strength, and if you see, it's 1.5% and 2.5%. So here also, because this could be because of the error, so almost the same strength. And at 0.6 water cement ratio, again, we have got the strength keeps on increasing. So this is how we got this equation. And again, just to refresh your memory, this is our conclusion, that we are able to reduce the strength, not reduce the strength, reduce the cement consumption, the economy, we can improve the economy by usage of ultrafine. And so that is it. Thank you.
Thank you very much, and I'm very thankful for managing the time, because I was getting a call from because they are starting the session. So because he has thankfully finished early, so there are some questions. If we can keep the floor open for questions. Yes, sir.
I'm not really quite familiar with your nomenclature. So ultrafine is ultrafine slag, is that correct?
Yes,
what is the average diameter?
Sir, before I answer you, I'm a big fan of yours. Dr. Suren Shah, sir. I keep on following your literature, and a lot of things I've learned from you. So thanks for asking this question, sir. Oh, ultrafine slag. the D50 is less than 5 micron. So in our slide, sir, we have given the, because of shortage of time, sir, I skipped that. So this is the result, sir. D50 is 4 microns. There is an Indian standard which has given a limit of 5 microns.
All right. Yeah, I wasn't familiar with.
Thank you so much.
Thank you. Any other question? Right. Maybe you have developed a good regression model, and I think you being RDC, lots of data, I think huge data you must have generated in years. It would be nice that now deep learning, maybe we involve some computer engineers also. It will give better predictions because that learns from your direct regression, right? So we are doing something, but we don't have large data. That's the limitation. But you being, maybe you take few years data, that would be huge and would be quite accurate in my opinion. So thank you very much. I thank all the audience and all the speakers. Give them a big round of applause, and thanks for attending this session, and I hope that we move quickly to the main hall where people are waiting for us. Thank you. Okay, please go ahead.
Thank you, and everyone.